these are copolymers. So just to save you guessing, these are what they are. For example, the car tires are, you have this styrene butadiene rubbers. They are the SBR, they're called styrene butadiene rubbers. They are essentially what your car tires have. Then you have this acrylonitrile butadiene styrene, ABS polymers. Acrylonitrile butadiene styrene, these are used in a variety of components in the car. And of course, these are the gloves, which is you have the butadiene acrylonitrile, which are the polymers that are used. So copolymers are much more common than what you think. We encounter them in all aspects of our life. And the idea with this copolymers is we want to get properties that are not accessible from either of the individual homopolymers or the components present. And here, the situation that we have is one is a very flexible polymer, the other is a brittle polymer. So you want to bring them together to see if you can have properties which are a blend of these two. So I'll just tell you the summary that we can copolymerize them. And because the polymerization is a living polymerization, you can prepare block copolymers. That means I prepare a polymer, at the end of it is still reactive, it is not dead. I add another monomer, from there the reaction occurs, and therefore you generate a block copolymer. And you can characterize them by many other techniques. And just to leave you with this idea of how does this entire process occur, where does the catalyst come in? So you can see the catalyst is a Lewis acid. That is, it can, therefore you can see the first on the top, there is this magnesium, and that magnesium can bind to the Lewis base, which is an oxygen, and that can be constituted as an initiation step in this. And once that happens, then the carbon adjacent to the oxygen now becomes electrophilic, and therefore the nitrogen that is present on the phosphorus ligand, that attacks this, and then you have a possibility of ring opening. And this initiates, the chain initiates, and you have a propagation. And finally, you can terminate this entire process by a proton, a protic source like methanol or something that terminates the polymer, and the polymer can be obtained away from this. So that's how this reaction occurs. So I'll just summarize. So what I've tried to show you is that there are for sustainable polymers, there are n number of approaches. One is recycling of existing polymers. We use them so that we don't have so much waste in the environment. B, you can use feedstocks that are renewable, and the polymers obtained from them are recyclable or they are biodegradable. And in that sort of an endeavor, we try to figure out if we can design ligands which can stabilize Lewis acids and which can do a variety of things. So our initial process was whether we can do this with other metals like yttrium, aluminum, zinc, etc. And they are useful in many catalytic reactions. After having ascertained that, we looked at them from cesium and magnesium to a specific purpose of polymerizing lactic acid and caprolactone, and finally co-polymerizing them. And of course, it's not that the story is ended. There are many challenges to this. And the challenges include, can you do this faster? Can you do it at lower temperatures? Can you access other types of copolymers, etc.? That's an ongoing process. Thank you very much.
Thank you, Professor, for that exciting talk. And now the audience may ask their questions.
Hello, sir.
This conversion.
A few hours.
Few hours.
Few hours. Yeah.
And what is the recovery percentage, or like recovery of the catalyst that you are using?
So the catalyst is used in very small amounts. And so what you could do is you could add more monomer to this reaction mixture already. And the fact that the monomer reacts further and tells you that you really don't need a large amount of this at all. So it's present in very small amount. So we haven't actually isolated the polymer, recovered that catalyst and reused it. But what was there in the reaction mixture, you add more monomer to it, it continues to react. Thank you. There is one question. Yeah, please.
Sir, you were supposed to discuss the stereochemical aspect of the catalyst as well.
The There's nothing like I'm supposed to.
Like,
I've just given a lecture what I wanted to.
no, sir.
So
Like,
if you have a question, you ask me.
no, sir. Like you showed that like the catalyst is selectively towards certain stereo.
Right. No, what I showed was that the polymer, the lactide, polylactide, can have different stereochemistries depending on the orientation of the methyl group. So what I didn't tell you is what is this final polymer? That's what the question
Yeah,
is.
yeah, that is.
So it's an isotactic polymer.
Okay,
Good morning, sir. It was nice presentation. So I would like to ask, if you are taking two different kind of monomers like polylactic acid and caprolactam. So how you are estimating the selectivity? Like this much monomer is forming this much polymer like that.
Can you repeat? I couldn't understand.
Selectivity for that block polymerization.
No, not selectivity. So as I told you, it's a block copolymer.
Yes.
So block copolymer means the amount that you add, if everything is going into the polymer segment, then you can actually modulate that. So imagine that you have a linear chain, and that linear chain is reactive at the end. So how much the length of this chain is dependent on you, that depends upon the amount of monomer you have added. And then from there it continues. How much you want to have in the further is again dependent on you, and that depends upon the amount of monomer you add. So that's the advantage of a polymer having a characteristic that is known as a living polymerization. So you could do that because of that nature. If it is not living, then there are, for example, if the polymer bites itself and forms a cycle and so on, then you don't have that control.
Then how we show the mechanism that this catalyst is having only, let's say, one active sites and you're taking two kind of monomers. So how the
Yes,
mechanism varies?
the catalyst has an active site in the form of a Lewis acid. The key thing is that at each point of time, the Lewis acid has to bind to something that is Lewis basic in the entire structure. So that could be, for example, the initiation step, it is the lactide that is binding to it.
Okay.
Then once the polymer grows, then it's the polymer end of the incoming monomer binds to this, and this polymer end which binds to the carbon, which is electrophilic, and that's how the polymer grows.
Okay.
Yeah.
Okay. Thank you.
hello. Sir, really interesting talk, sir. Sir, I got some idea, like I wanted to discuss that. If we are taking racemic lactide,
Yes.
and if there is a catalyst that is enantiomer specific, definitely it can lead to the polymerization of one enantiomer and another may remain as such. So at the same point of time, you would be getting a chiral polymer and a particular enantiomer of lactide.
No, if you take a racemic, you will not get a chiral polymer.
Means it is means the catalyst itself, if it is chiral, it will selectively
Correct.
polymerize
Yeah.
one
Right.
and another. That can occur.
Is giving me a research idea.
Yeah,
that's
yeah, and if we try calcium, would it work?
Actually, yeah. See, between magnesium and calcium, magnesium is better in terms of its reactivity and also equally environmentally friendly, like calcium.
Yes, yes.
That's
Thank you, sir.
I had a bit of a silly question.
Yeah, please.
This is about the polythenes that we buy from the market or they are given. So there is some thought that the thin ones are bad for the environment and the thick ones are not so bad.
Yeah.
That's the feeling that we are given. So I don't understand this, A. And B, I don't also understand what is the structure of these, across the thickness of the polythenes. So these seem to be chains, but are they also chains in the across the thickness or?
Yeah. So the first thing is the lifafa that we use. The lifafa is a low density polyethylene. So it has got a polymer backbone, and there are many side chains that are present. And that happens because there is a transfer of polymerization to the side chain. They're very reactive, and this is typically done by what is known as a free radical polymerization. And this free radical polymerization generates such polymers where the chain is not straight, but there are many branches to this chain. And therefore the question is, you have therefore one chain and there are branches, and the branches could have further sub branches that are there, and that because of that the crystallinity of the such polymers is low, and because of that their melting temperatures and glass transition temperatures are low, and that's why the mechanical strength also is low, and therefore they're used for that purpose. The ones that are linear, completely linear, are the ones which are the high density polyethylene. And this high density polyethylene therefore has applications which are somewhat more sophisticated than the simple applications that are there. And even higher is this ultra high molecular weight polyethylenes, and some of them are purportedly in one particular direction stronger than steel. None of these are biodegradable. Now, all of them, because what you have is a carbon-carbon bond and a carbon-hydrogen bond, and none of them are readily degradable at all. And in fact, they can live for many, many years unless there is a free radical source that cuts off the hydrogen and that decomposition is accelerated. But still, they will be in landfills for several years.
Hello. Hello, sir.
Yeah, okay, talk. Okay, yeah, sure.
Yeah. So first of all, sir, thank you for the nice presentation. So since it is a living polymer, so how do you stop it when the reaction is end?
So yeah, you can stop it by some, I told some protic source.
So you have used some.
You have to kill the polymer.
Okay, so you have used some chain
So
stopper.
methanol. You can use methanol.
Okay, and what is the molecular weight? Weight average molecular weight?
We haven't, these polymers, all of them have molecular weights up to about 15,000, 20,000.
For 50,000.
15 to 20,000.
20,000. Yeah. Okay. And sir, my third question is, you have selected cesium, magnesium, so maximum they are alkaline earth material.
Correct.
So is there any specific reason why you did not choose any transition metal, because they have a multiple redox state?
We are not using any redox property here.
No, I'm sir asking that if I am using transition metal element, so there may be a larger number of binding site.
No. Firstly, the reactivity is not because of the variable redox states of the metal. That comes in different types of reactions. When you have an oxidative addition reaction, or where the valency of the metal changes. No redox properties are required here. It's just a Lewis acidity. Then, in terms of the capability of the Lewis acid to have the polymerization around it, as long as it's a good Lewis acid, it's good enough. Second thing is, how many can it accommodate the monomers and the growing polymer chain around it? That is the sort of a premise behind this choice.
Thank you, sir.
So thank you for this wonderful presentation. So a very nice question. So most of the times we use this peer-led ABS for 3D printing. So when you combine different kind of polymers, is it 3D printable? Like I
don't know. I don't know whether the combination must be, but I don't know what proportions will be deleterious, what are good. I cannot comment on it.
But even the renewable polymers should be prepared.
Yeah, they can be 3D printed. Yeah, that is
they can be 3D printed.
They can be 3D.
Thank you, Professor.
Yeah.
Thank you, Professor. So this is Saravanan from IIT Trichy. I'm working on civil engineering and waste management. So I'm really concerned about the product what you have made. It's really renewable. And one more question is the property of the material. We have shown like the melting point is around 60 degrees Celsius and all. So
no,
where can
there
it
are two
be?
melting points I showed you.
Yeah.
The caprolactone is the melting point of 60 degrees. The polylactic acid is around 200 degrees.
So where can we really apply this product?
Well, no, as we are speaking, these are in products. They are used in various products, but they are not replaced polyethylene terephthalate. They are used as products.
So this copolymer is also
the copolymer is not yet.
The copolymer is biodegradable actually.
The copolymer is biodegradable. Now, I should qualify what is biodegradable. If you, for example, take it and just leave it outside, it won't. They are degradable under what is known as industrial compost conditions. That means around 60 degrees centigrade, they will degrade.
Okay, so now I invite Professor S.C. Leela, PMRF Nodal Coordinator for Broad Area Interdisciplinary from IIT Bangalore, to kindly come up to the stage to felicitate Professor V. Chandrasekhar.
Thank you. Thanks a lot.
So now it's time for the lunch break. We will reconvene at 2 p.m. for our next plenary talk.
बहुत सारे गिफ्ट दे दिए भाई आप
Hello. Hello.
we're trying slowly. That we must have started from 5 we will enter.
Oh, you are coming, is it? Very good. I am also planning to come next. So that you should. I came before you. Really? Okay, last year I came, but last year not complete. I never been to anywhere. Actually, this is excellent. Rather told me that. Welcome back, everyone. We hope you had a refreshing lunch. Now let's dive back into our plenary sessions. It is our pleasure to introduce our next speaker, Professor Sanjay Mittal from IIT Kanpur. Professor Mittal is a distinguished professor in the Department of Aerospace Engineering at IIT Kanpur. He is a leading expert in computational fluid dynamics, aerodynamics, and fluid structure interactions, with groundbreaking contributions to high speed aerodynamics and vortex dynamics. He earned his PhD in aerospace engineering from the University of Minnesota, USA, and joined IIT Kanpur in 1994. Professor Mittal has developed high fidelity CFD techniques that have been instrumental in aircraft design, wind turbine aerodynamics, and high speed train optimization. He is a fellow of the Indian National Science Academy, the Indian Academy of Sciences, the National Academy of Sciences, and the Indian National Academy of Engineering. His exceptional contributions have been recognized with prestigious awards, including the Shanti Swarup Bhatnagar Prize in 2006, G.D. Birla Award for Scientific Research in 2015, and the J.C. Bose Fellowship in 2013. Let's give him a warm welcome as he comes up to the stage.
Thank you very much for that very generous introduction. Uh, so I'm very pleased to be here, and thank you to all the organizers. When Professor Murthy called me, I was absolutely delighted. I don't want to miss any visit to your beautiful campus in Hyderabad. Can we have the slides, please? 1 minute. Okay. So I am in the Department of Aerospace Engineering, as you already know now. But there's a little bit of side work that I do, and this is one of them. So I have a lot of interest in sports. I'm myself a badminton player. I may not look like one, but I get my way around. Uh, and I also watch a lot of other sports. Okay. So we started this work several years ago, almost a decade ago. And the irony is that there is no PhD student who has worked on it. So although I'm presenting it here, but I was always a little bit worried whether something useful would come out of it. So all the students who have worked on it are either undergraduate students or master students. So the color coding is the whites, they are masters, and the orange ones are the undergrad students. Okay, a lot of them. So the first question that we tried to address is, this has been going on for a while. Uh, how do these different sports compare? So if you look at projectiles from, let's say, varied sports, um, can we get data for them as to what is the air resistance they offer? So just to look at the energetics, if I'm a player and I want to spend some energy on moving these projectiles, then drag typically varies as velocity squared, and the power required would vary as velocity cubed. Okay? So a good number would be the drag coefficient. So drag coefficient is essentially the drag on the projectile, which is non-dimensionalized by the dynamic pressure, which is rho v square, and then also the cross-sectional area of the projectile. So we wanted to take all these objects and put them on a chart as to which one is how much air resistant. So something like this came up, which was very satisfying. So the x-axis is the Reynolds number, which essentially you can think of it as a proxy to the speed. But the different projectiles operate at different speeds, so it is kind of a non-dimensional number. And the y-axis is the drag coefficient. And you can see all kinds of projectiles here. So for example, the badminton shuttlecock has really the highest drag. Okay, so that's why you see these games last very short. Okay, you spend a lot of energy. On the other hand, if you look at something like a golf ball, which is the lowest curve here in solid blue squares, so there you have a high drag coefficient at some speed, but then at the speeds at which the golf ball operates. That is usually the drag is very small. And I'm going to say a few words. And then you have other sports. For example, the tennis ball. So that those are the green triangles. There's a lot of contribution to the drag from the felt of the tennis ball. And I don't know how many of you watch tennis. So you must have seen when a player is about to serve, they request for several specimens from the ball boys or ball girls, and then they pick one of them. And I used to wonder, is this a fashionable thing to do, that the more you choose from, the better player you are supposed to be, or there's some science to it? So it turns out that the drag depends very profoundly on the felt. Okay, if it's a tight felt, that means it's a new ball and not being manhandled. Then it's going to go fast. It will offer very little resistance, and as the fluff goes bigger, it spreads out. Then the air resistance will increase. So for the same force, your serve would come slower if the ball is a little bit older. But then as the ball becomes older, the felt wears off, especially on a clay court. So by the time the balls are changed, again their drag goes down. So it becomes very technical. And apparently the players know all this, okay, but they just haven't put it down. Okay, so what I want to talk about today is just specifically two projectiles, and time permitting, I'll show you something about frisbee. So I want to talk about the aerodynamics of a cricket ball. Specifically, the questions are about swing and reverse swing. So I'll try to explain to you in my way what is meant by swing, what is meant by reverse swing. And then when I used to watch these cricket matches, commentators would often say that now that the ball is becoming old, it will start reversing, which automatically implied that a new ball cannot reverse. Okay? And that intrigued me. Why should a new ball not reverse? Okay, which means what is the phenomena for swing and reverse swing? So they're all connected. So we'll try to address that. And then, of course, I'll tell you a little bit about badminton shuttlecock. I think, in my opinion, this device, the badminton shuttlecock, is one of the most innovative devices ever. I mean, it's the amount of engineering which goes into it is absolutely magnificent. I'll say a few things about it. Okay, so first we'll begin with the shuttlecock. So he's my favorite player, Lindan. I don't know how many of you have seen him play. He's really a legend. Um, so just to give you a background, the duck feather shuttlecock, which is shown below, is made out of 16 feathers, and these feathers are hollow, and therefore they are very light. This weighs only 5 grams. I don't know how many of you would have guessed it, okay, but just 5 grams. The problem is, if you want to now replicate this with a synthetic shuttlecock, it takes only 5 grams to manufacture this device. You cannot change the size, it should look exactly the same, it should weigh the same, and it should have the same trajectory as a feather shuttlecock. Okay. Typically, the cork is about 2 to 3 grams, including the ribbon. So for the skirt, you have about 2.5 grams of nylon, and you need to distribute that you get, which is a shuttlecock, which doesn't break too easily, and it also gives the same aerodynamic properties. So one of the questions was, why do these things behave differently? What is the aerodynamic difference between them? And as you know, the fastest smash could be as much as excess of 550 kilometers. Right? It's one of the fastest moving projectiles. So there were some bright UG students who came for some summer project. I said, okay, these are. So I gave them some specimen, and I said, you make AutoCAD models out of them. And they made an AutoCAD model out of Amaze 350, the Yonex, which is on the left. Then the center one is the feather shuttlecock, Aero Sensor 50. And then I said, okay, why don't you also make a solid skirt without any gaps? So it's hollow inside, but there are no gaps in the skirt. Okay? And my guess was that the shuttlecock, which has no gaps, that is the most bluff, and that would create the maximum air resistance. Okay, so that I thought I will give it to them so that it's like a consistency check. So of course they went through all these calculations, and to cut a long story short, this is the kind of flow they were able to simulate. So this is the speed of the flow at a cross section. So you can see the flow is coming from below the shuttlecock going vertically upward, or you can imagine that the shuttlecock is going down, flying down. So it's just a change of frame of reference. Okay. And clearly the color here is that red is high speed, blue is very blue is kind of negative speed. So there's a big recirculation zone for the last picture, the rightmost, and that's the solid skirt. And that seemed like the largest drag. But then the numbers freak me out. Okay? So the gapless has the smallest resistance, and the feather is somewhere in between, and the synthetic shuttle has the largest drag. Okay, this was very intriguing when we first got the results. And then, of course, we did a lot of work, and it turns out that the gaps they play a very important role in generating drag. In fact, they're of use in aerospace also because many missiles and some low-cost UAVs they have grid fins. Okay, so they generate aerodynamic forces through actually porous kind of structure. So it turns out if you have a shuttlecock here, then the pressure difference on the solid surface on the inside and outside, a component of that generates the drag, and that difference is much larger in some shuttles compared to the others. Okay, so that's the reason. So, couple of things that did not become clear. So we were able to simulate and explain a few things. Uh, what is the mechanism of drag generation? Okay, so we had some hypothesis. But the bigger question was, how come Yonex has not been able to give out a shuttlecock that matches the drag of the feather shuttlecock? I mean, they invest so much money, so there must be a reason why the drag on the synthetic shuttlecock is larger. So we went back to the wind tunnel again and did some tests. So shown here on the bottom frame is a test in the wind tunnel. So you put this on some kind of a balance. So the red colored device is a sting. Downstream of it is a balance. You measure all the forces, change the flow speed, and you have your data. So in the plot above, the vertical axis is the drag coefficient, and the x-axis, on the upper x-axis, you see the speed of the shuttlecock in kilometers per hour, and then it's non-dimensionalized to give the Reynolds number. Okay? So you can look at capital U, which is the speed. So if you look at the feather shuttlecock, which are the solid reds, you'll see they're almost flat. So the drag coefficient doesn't really change much throughout the speed. And neither does the shape of the shuttlecock. These feathers are fairly rigid, okay, so they retain their shape. But look at the synthetic shuttlecock. Okay. It has a high drag at low speed, and then by the time you hit a smash, it kind of deforms. Okay, so the frontal area reduces. It's very fast. So by the time you go to about 200 kilometers per hour, you see it's no longer circular. It has a square cross section, and the drag has really reduced. So what that means is, if with the same power I hit a smash with the feather shuttlecock, it'll it'll face the same resistance throughout. Okay, the same resistance, the non-dimensional resistance. But if I did that to a synthetic shuttlecock, the drag would reduce, and it would fly faster, and the opponent would have less reaction time. So a smash would be more difficult to play with a synthetic shuttlecock as compared to a duck feather shuttlecock. This also answers the question, why is the drag higher for the synthetic shuttlecock at low speeds? Because Yonex is smart. They wanted to tune the shuttle. Okay, so if they kept the drag same at low speed, then by the time you hit a smash, this drag would be really low. So they came up with some speed at which people really hit. So 100 kilometers per hour is actually a very strong smash for people like us. I mean, I had my students hit smashes and we measured their speeds, and we barely went beyond 120, 130. Okay, so that's pretty good. So that's how these devices are made. Can we predict these? So the next thing we did is we tried to do what is called a fluid structure interaction. So as you will notice, as far as this yellow synthetic shuttlecock is concerned, it changes its shape in flow. Okay. So can we couple the fluid mechanics to solid mechanics and then do it kind of in a coupled manner and actually generate these shapes? So that's the next thing we did. So we generated a mesh for the shuttle. So that's the structural mesh. And then there's a fluid dynamic mesh. You couple them. So at each time step, you would be solving the fluid flow, you get the forces, you push them back into the structural code, you get the deformation. Now the deformed shape, you compute the flow again, and then of course you repeat it with time. So it's a little bit of a messy calculation, uh, but it was done, and you can see the spontaneously actually you are able to get the buckling of the skirt. So on the left you see a shuttle at a very low speed, so the cross section is almost circular, and then on the right is at a slightly higher speed, and you can see the square cross section almost coming up spontaneously. In fact, what we found is if you plot the drag versus speed, so you can only look at the red curve, you can ignore the others. So the drag reduces with speed, and at some speed, the shuttlecock buckles, and you get a very massive change in the drag. And then if you hit even a faster smash, then actually the shuttlecock actually vibrates. Okay, so we saw that in the wind tunnel as well. So it starts flapping. And then if you increase the speed even further, then you get something like a traveling wave which goes around, and it's really very beautiful. So here are some pictures. So we are looking at a shuttlecock which is facing us. So imagine the phone behind the screen, and the shuttlecock is facing you. So at 30 meters per second, it's almost a circular cross section. The coloring is zero deformation is blue color, and red about 2.8 is the red color. And then as you increase the speed, of course, the deformation of the shuttle increases, and then the skirt buckles, and finally you get a traveling wave and so on. If you compare this with experiments, which is the real test of this simulation, the black line is from the wind tunnel, and then we chose different material properties for the nylon because these nylons, their property also changes with temperature. Okay, so in Kanpur, it would behave differently as opposed to maybe in all India, England, and so on. So the best data fit that we got is the blue color, and it looks like the model is doing reasonably well. So right now we are trying to now change the geometry of the shuttlecock and see if we can come up with a better design. But there's a lot of work to be done in that. Okay, now I change gears. We move to cricket, probably more exciting to a larger number of people. So if you're a bowler, the task is simple. You want to deceive the batter, okay, and there are many ways of doing that. One is just to bowl very quick. Okay, so the batter has very little reaction time. So somebody like Shoaib Akhtar, or we have a lot of Indian bowlers as well. The other one is of course spin bowling. So in spin bowling, you could have two kinds of lateral turns. One is off the pitch, where the ball hits the pitch and then it turns, and the other is in the air because the ball is spinning. That's a Magnus effect. So sometimes you'll see bowlers where the ball is actually turning in the air, and that's very deceptive. So when they loop it, and it's also turning. We'll not talk about that. The next one is the seam bowling. So in my generation, it was people like Venkatesh Prasad. So they would hold the seam vertical, and then it hits the deck, and even the bowler usually would not know whether it goes to the leg or to the off. Okay, so how can the batsman know? And some people can control. So Bumrah controls it very well. I don't know, it's absolutely magical. So he knows which way the ball will go with his cutters. We'll not talk about that also. Today we'll talk about swing bowling, okay, where the bowler puts a backspin on the ball. So you can see the grip over there. So when the bowler releases the ball, actually it spins in a manner that the upper surface is moving towards the bowler. So that's called a backspin. And the seam would be in a vertical plane, but it's either facing the leg stumps or the off stump. Okay. And you could have different terminologies: in swing, out swing, reverse swing, or a conventional swing. I'll explain that. So here is what the general understanding is. So if I'm a bowler and I hold the seam, let's say towards the off stump for a right-handed batter, that's the yellow line. So if the ball will always move in the direction of the seam. Okay, and I'll explain you why. So because of the way it is bowled, so that's an outswing. If I bowl in the blue trajectory, then that's also moving in a conventional swing because it is moving along the direction of the seam, but that's termed as an in-swing. So for the purpose of this talk, we will not differentiate between in-swing and outswing. Both are conventional swing for us. Okay. Now, if I am a batter, an intelligent batter, somebody like Sehwag, I will watch the bowler, okay, and I will see how they release what is the seam position when they release the ball. And from the seam position, I can make out whether the ball will go to the off stump or the right stump, and then I can hit it. Uh, but what can sometimes happen is it can reverse. So instead of going in the direction of seam, it will go in the other direction, and then hell will break loose. So an example is given here. The blue line is the ball going in the direction of seam, so that's swing bowling. But if it goes in the other direction, that is reverse swing. So that's particularly if you are bowling at a high pace, then the batter has little reaction time and it could be devastating. So we need to understand a little bit of fluid mechanics to be able to understand this. So please bear with me just a few concepts. Okay. So if I take a sphere, okay, and I throw it, of course it will face some air resistance, and that we call as drag. Okay. So typically, if you look at the x-axis, that you can think of as the speed, and the speed is a proxy to the Reynolds number. So it is defined as, so if I take air, so density of air is fixed, the viscosity is fixed, the diameter of the sphere is, of course, you have the sphere. So Reynolds number just varies linearly with speed, that's the x-axis. The y-axis, the blue color is the drag coefficient, which is actually the drag force divided by the dynamic pressure and the frontal area of the sphere. I've also plotted the drag force itself in red color. Okay, uh, so, so story is like this. So if I throw a sphere in air, then the drag on it increases almost quadratically with speed. So it's almost like a parabolic increase with speed, up to a certain speed. If I throw it beyond a certain critical speed, then the drag reduces, which is strange. Okay, so the faster I want to go, the less energy I have to spend beyond a certain speed. And this is very well known. This is known as the phenomenon of drag crisis. And that's because the boundary layer goes from a laminar to a turbulent state. So you will see two insets here. The bottom one is a laminar boundary layer where the flow is very smooth. There is not much mixing in it. And if you see on the upper right, you will see a turbulent boundary layer where there is a lot of mixing inside the boundary layer, and therefore the separation is delayed. Okay. So the turbulent boundary layer in this case would give us lower drag, a lower, narrower wake, and a laminar boundary layer, of course, gives us more drag. Okay, so we'll remember this. I also request you to remember that this transition for a smooth sphere happens at around, you know, uh, 0.3 million or so. Okay. So of course, the speed would depend on what is the diameter you have taken and what is the medium that you have taken. But we'll remember this number, around 0.3 million. Okay, so there is proof for this that how does the boundary layer become turbulent? So on the left side, you have a flow where the boundary layer is laminar. So we can actually visualize this. So if I take a sphere, a black color sphere, and put a film of oil on it, and the oil has a dye in it, a white color dye, and then I put it in the flow. So all the dye is, all the oil is pushed downstream, and the place where it separates, all the oil will collect because you know then the flow has reversed its direction, so I can find out where the flow separates. But when the boundary layer becomes turbulent, then you can see it is dragged, it's more black for a more downstream distance. And then there's also something called a laminar separation bubble, LSB. So something funny happens. The flow separates and then it reattaches and it separates again. So the final, the TS is the turbulent separation point. That is far downstream, almost of the order of 120 to 130 degrees, as opposed to almost 80 to 90 degrees for a laminar separation. Okay. So one way to reduce drag in a body like this, not an airplane, but a body like this, a bluff body, would be to make the boundary layer turbulent. Maybe I'll skip this. So what happens if I make the body rough? So instead of having a smooth sphere, what if I have a rough sphere? The phenomena remains the same, just the point of transition where the boundary layer becomes turbulent shifts to a lower speed. Okay, so that's also intuitive. So if I have a rougher body, then hopefully the boundary layer would become turbulent earlier, and I would get this reduction in drag at a lower speed. But the bad news is that the final reduced drag increases as I increase my roughness. Okay, so you can't have everything. So that's the price you have to pay. Now, I told you that for a smooth sphere, the transition happens at around 0.3 million, but cricket and golf balls, they operate at something like 0.1 million. And that's because now you see the roughness becomes very important. So cricket balls, golf balls, they are rough. So that's the operating. So let's look at some specimens. So there's a cricket ball, there's a baseball, and there's a golf ball. You will be surprised with the size of the cricket ball and golf ball. It's almost identical. Two different continents, they came up with exactly the same design. Baseball is thrown underarm, so it has a little bit higher speed. So the Reynolds number is a little bit larger, but you know, of the order of 10 to the fifth. Mass is about the same, 150 grams. Golf ball is much smaller, but it travels at higher speed, but the typical Reynolds number is 2 into 10 to the fifth. Now you know why golf balls are dimpled. Okay, so we are artificially trying to make the boundary layer turbulent so that when it is turbulent, for the same force, I would have smaller air resistance and my ball can travel farther. Okay, so playing golf is, you'll have more time for networking, more people to talk to. So it's a great. Okay, so the first thing we did is we put these SG test cricket balls, brand new ones, in a wind tunnel. Okay? So the most educational picture is the bottom right. That's a top view. So there's a flow coming in. So the ball is stationary. So you can imagine the batter is downstream of the batter is upstream. Okay, and the ball is traveling towards him or her. But in the test, of course, the ball is stationary and the flow is coming in. So I can change the seam angle. That plays a very important role. And I can change the wind speed. So the first thing I want to do is collect data that what is the force. So we would be interested in the force, lateral force. That would be the swing force. Okay. Of course, drag is also important, but swing is the one which is most important. So we are interested in how does the swing force change with speed and with the seam orientation. Okay, so here is another picture. So imagine the ball is coming towards you, little bit scary, or the flow is going in. So you can see that if the ball is coming towards you and it moves to the right, that would be a conventional swing, so we'll call it a positive force. If it goes in the blue direction, we'll call it as the reverse swing, and that's written in the, so that would be negative. There are other forces as well, so there's a lift force on the ball, there's a drag, but I suppose that's not so important. Okay, so these are the first set of measurements that, reliable measurements that we obtained from our wind tunnel tests. So the x-axis is the Reynolds number, which is the proxy to speed. Y-axis for the upper picture is the drag. We'll forget about it for the time being. We'll focus on the lower picture, which is the swing force coefficient. Positive is conventional swing, negative is reverse swing. There are 3 or 4 curves here. That's because when we started doing the experiments, we realized all balls are handmade, so you cannot repeat the data. So you put one ball in the wind tunnel, a few days later it changes a little bit, you put another one, it is completely different. So how can you do experiments with that? So we started 3D printing the ball with the seam on it. Then we put some pressure ports inside it. So I request that we focus only on the cricket ball, which is the blue line. The others are very similar, just the Reynolds number is different. So we'll focus on the blue line. So if we start with a certain seam orientation, which is 30-degree here. So at very low speeds, actually the boundary layer is very thick, and the seam has a certain height. It doesn't really affect the flow as much, so there is no swing force. So you are bowling somebody like Kumble. Kumble is actually very fast. Even maybe somebody like Varun Chakravarti, maybe a little bit slower bowling. Okay, so you would get no swing force. Then you start increasing the speed, and then you suddenly see the swing force actually builds up, and it saturates, and boom, suddenly it becomes negative. Okay, so there's a reverse swing. So this is a new cricket ball. So let me summarize the phenomena for you. As a bowler, I would see as I keep increasing my bowling speed while maintaining the seam orientation, low speeds, no lateral movement. As I increase the speed, I start getting swing, it saturates, and then finally I get reverse swing. So what is the fluid mechanics of it? If you look at the upper picture, the cartoon of that, so there is a seam side. So if you look at the flow direction, it goes over the seam. So I'm calling that as the seam side. Then there is a lower side, which I'm calling as the non-seam side because the flow doesn't hit the seam first. So the boundary layer becomes turbulent as it hits the seam side. And as I showed you earlier, it stays attached and the separation point moves downstream. So you get more suction there as opposed to the lower one, which is still laminar, and you get a force in the upward direction, and that's the swing force. But as you keep increasing the speed, somewhere even the smooth guy is going to become turbulent. Okay, so as the bowler keeps increasing speed, the upper surface, the seam side is already turbulent. Now the non-seam sides become turbulent, but the non-seam side became turbulent through a natural process that is a forced one on the seam side. So this suction, the natural one is a little bit larger. So now you get a force in the downward direction. Okay? But that force is relatively smaller. So if you look at the coefficients, it's about minus 0.15 in the blue line, whereas for the negative, and it's about 0.35 for the swing force. But again, the speeds are larger, so the force has to be multiplied with rho v square, so you still get a reasonable force. So that's the story of swing and reverse swing. So it already tells us that a new ball can reverse swing. Of course, the ball has to be delivered at a very high speed. So if you make a very good quality ball, okay, uh, then the bowler has to really bowl very quickly to get reverse swing. As it becomes older, the surface roughness increases, and therefore you can get swing at a lower speed, which I will show you in a minute. These are some flow visualization just to show you what is the physics, but we'll skip that. We did some pressure measurement, we did some PIV, I will skip all this. So all this seemed reasonable, but there was one question which we could not answer. I mean, there are many, but there's one which really bothered us. If indeed the seam is causing the boundary layer to become turbulent, then how come the force is increasing gradually? So if you look at the green line or the blue line, it builds up gradually. Common sense would tell us if the boundary layer is turbulent, then it should be just a step function. So either there is no force or there is a swing force, so it should just increase abruptly. So why is it going gradually? And we could not get this data from the experiment. We tried analyzing whatever we had. So we had to come back to computations. So again, we made these models, smooth sphere, 1 seam, 3 seams, 5 seams. So that's a good impression of a real cricket ball. And we did the smooth sphere, so we were able to ensure that we get a turbulent boundary layer. I will not bore you with the details. Then we went to the cricket ball. Okay, so we were able to resolve the seam. So now we have to look at the disturbance caused by the seam. So the mesh has to be really fine. So this is like 80 million elements, very fine mesh. We put it on our finite element code, which is in parallel, so it scales up very nicely. So we can do these calculations in parallel. And we got these flows, but I will show you the summary of this. Just to show you that experiments and numerics, they have some correlation. So the last picture, the right one, is from the oil flow visualization from the experiments, and the other two pictures, the one on the left and the center frame, they are from the CFD, and you can see the flow structures are remarkably reproduced. Okay, so they are bang on. So this is what we were able to find, okay, from the calculations. We were able to replicate the experimental data, and to our amaze, what we found is that in the initial stages of swing, which is actually the yellow color region, the boundary layer does not really become turbulent. It is still laminar, but just the disturbance is large enough that it is delayed, and then you get transition to turbulence. So this was a little bit fancy. And this was a picture that I like a lot, and it came on the cover page. These are some more pictures, which I'll skip. Okay, maybe this would be of more interest. Suppose I am a bowler, okay, and how does the ball reach? What is the state of the ball when it reaches the batter? So the air resistance is slowing down the ball. Okay, so by the time I release it and it's undergoing drag, so the speed which the batter encounters is about 10% lower. Okay, it has slowed down. So really speaking, if I want to understand the trajectory of the ball, if I want to use this data, I should go towards the origin. So I start by bowling at a large Reynolds number, and as the ball goes towards the batter, my Reynolds number reduces. That's how I should interpret it. Now let's take two stadia. Maybe somewhere in Kolkata, there's the temperature, Lords little bit colder, and then you have the air properties, they change, the viscosity and density. So we'll take two bowlers. Um, let's say one is somebody like Ganguly. So I'm choosing bowler from my era. So he bowls at Kolkata at 80 kilometers per hour, and he bowls at Lords, exactly the same action, exactly the same speed. Okay, let's see what he does. So first, Kolkata, his Reynolds number is of the order of zero point 0.8 into 10 to the fifth. Okay, so zero point 0.8 into 10 to the fifth would be somewhere here. Okay. So he gets a swing. So he swings a little bit. He goes to London, exactly the same thing, but his Reynolds number is 1 into 10 to the fifth, somewhere here. So he swings more. And one would expect that this is the London effect. Okay. Maybe it is, but it's all aerodynamics. Okay, it's not that he's more encouraged in London or anything. It's just the weather. Same thing if you have an overcast condition. So overcast means the humidity will be higher, so density would be lower. Water vapor has smaller density than air. Okay, so your Reynolds number will be lower, and it could do strange things. Let's look at somebody like Bumrah. So he bowls at 145. So in Calcutta, his Reynolds number would be something like 0.15 million. So you can see he gets very high swing. He goes to London, he gets close to 2 into 10 to the fifth, so he starts reversing. Okay, so same bowler, everything is same, just the weather conditions can be used to get these different things. There's something more that came out of it, which is the following. In airplanes, which also generate lift, okay, I mean airplanes better generate lift. So the way they generate lift is you have suction on the upper surface and you have a higher pressure on the lower surface. But at the wingtips, the flow kind of leaks, okay, from lower to higher pressure, and then you can get these very nice wingtip vortices. It turns out you can get the same thing on a cricket ball. Okay, so you have the seam surface, the seam side, you have lower pressure, the non-seam side, you have higher pressure. So actually the flow could leak and you should get wingtip vortices. So we looked for them, and sure enough, we saw that there are wingtip-like vortices in cricket ball, and they would change the polarity if you do reverse swing. Okay? Now, the implication of that is if I'm a fast bowler, okay, and I bowl a bouncer to an aggressive batter, so when it whizzes past the ear, okay, you get this extra signal, and which I think perturbs people. So it has a zing factor to it. Okay, these are just some more pretty pictures. I don't know how I am doing on time. I must have exceeded my time. 5 minutes? Okay, thank you. Okay, so we can actually we can estimate the trajectory of the cricket ball now, okay, by using all this. So we have the data, and by assuming quasi-steady, we have the forces, we can just integrate the Newton's law of motion and actually get the trajectory. So you can see different, so this is a ball moving over the pitch, and the lateral displacement it showed here. So at 90 kilometers per hour, you get a very large swing of the order of almost a meter. Okay, and then as you go to something like 150 kilometers per hour with a new ball, you can get reverse swing, which is also shown here. In between, it does a very strange thing. It first does a reverse and then swing again, because remember the Reynolds number is changing. Okay, so it starts with a high Reynolds number, it reverse swings, and then again straightens out. Okay, so you can get a curve ball kind of a thing. Many people think that the faster you bowl, the more swing you can get, but that's not true. Okay? Actually, the air remains airborne for less time if you are bowling quick, because it just reaches the pitch very quickly. So there's an optimal speed. So 90 kilometers per hour is about the speed where you can get maximum swing. Okay, but players also say that it's not the, the amount of swing which is important. It is the variation and so sometimes smaller swing with just is playing around with the bat that is more important. So that's where the skill comes in. Maybe I'll skip this. You must have seen, the bowlers. They take a ball and then they kind of shine it, okay? And so that's called contrast swing. So what they typically do is the team will decide. Uh, you see, this ball has a monogram. So, for example, the SG ball will have SG written on one side but not on the other. So the team will decide, and there's a way they do it, that which side they will keep shiny. So they keep spitting on it, polishing it, sometimes in the front, sometimes at the back. I talked to some players which one is better. I could not get a satisfactory answer. So those of you who want to do a research on this, which is a better way to polish a ball, I think it's a fantastic topic. Uh, so we wanted to do some tests on this. That what is the effect of this so-called contrast swing? Okay, and it is really nice. So we took a new ball and we sandpapered one side of it. Okay, so that's the second frame, the center frame at the top. And then we kind of change it around. So you get the third frame. So all this is being done with one specimen because there's a variation from one ball to the other. The question we are asking is, typically if the team has decided to uh, do this contrast swing, then how does it change with these different kinds of strategies? Then you also rough the seam. Okay, so that's the last frame, the rightmost frame in the second row. Then you reverse it the other way, and then you get a completely rough ball. Okay. So now imagine the second column, the top row, second column. You already have the seam, and you also have, in addition, the roughness on the top. So intuition tells us that this boundary layer will become turbulent earlier. So this ball will swing earlier, and most likely it will also reverse swing earlier. The second one is the third one rather. The rightmost top row is more interesting because now you have a competition. Okay, there's a roughness from the seam, and there's a roughness on the lower surface, and now interesting things can happen. Okay. So I'll show you the data. So the red line, the red circles, those are from a brand new ball, and look at the magenta line. Okay, that is the non-seam side is roughened, and you can apparently get a reverse swing at 50 kilometers per hour. So spinners can get reverse swing. Okay, so sometimes in one-day matches, um, you could have spinners getting spin as well as reverse swing. Okay, so I don't know how many of you are familiar with baseball, but please look at the trajectory of the ball first and then the reaction of the batter. Okay, they have no clue what's going on. It's just going in a zigzag motion. Okay, and that's a knuckleball. So the idea is that in a traditional baseball, they will put very little spin. So they will they will pitch the ball with knuckles so that it doesn't spin. And then because of the seam orientation, it still does a very small spin, about one RPM, sorry, one revolution for the entire pitch cycle. And because of the seam, it kind of does a zigzag motion. Now in cricket also, they call it a knuckleball. You must have noticed the commentator. My take is it is a Hindi knuckleball. Okay. the, actually, it doesn't do a zigzag. I've seen many footages. Nowadays, they collect data and you can retrieve it, all the trajectories. So none of them, barring one or two, they don't really follow the zigzag motion. So I wrote to BCCI that I could propose a knuckleball, and of course they laughed it off. So we published it. So you could try it. So the proposal is the red trajectory is how today the knuckleball is being bowled by our Indian cricketers. But if they just change the grip a little bit, so instead of the spin being in in a horizontal axis, if the spin was in the vertical axis, which is also a skill, then they would get a zigzag motion. Okay? And they would get unplayable deliveries. So I don't want to take your time. This also came in Indian Express. Just to show you, you could get trajectories like this. Okay, so again, this is the top view of the ball along the pitch. It can do a really zigzag motion. So if you bowl this at 90 kilometers per hour with this kind of a variation, virtually unplayable. Finally, some stuff on frisbee. So this we have started about 2 years ago. So the idea was to look at the flow on a frisbee and what is the effect of spin. I don't know how many of you have thrown a frisbee. Can you throw it without a spin? It just wobbles and falls down, right? So of course it is needed for gyroscopic stability. But then what is the role of the spin on aerodynamics? How do the force coefficients change? That's the question you're asking. So we did all these calculations. It's really a fluid mechanicist dream come true. You have all kinds of interesting flow structures. You get very big laminar separation bubbles. You get wingtip vortices. But I'll just show you the final slide. So the first column is no spin, and the second column is with spin. And even though the flows are very different, qualitatively different, but magically the forces are very comparable. So I don't know what to make of it. All right, so thank you very much for your attention. I'll stop here. I'll leave with some conclusions.
Thank you so much, Professor, for that impactful talk. Now we'll take some questions from the audience.
I thought he raised his hand first, so maybe can we? You are far away, so it will take you more time to come and get me. If he's angry, he will jump right away.
Hello, sir. Thanks for a very insightful talk. So I'm Sai Vinay from IIT Madras, working with Professor Mahesh Panchagnula, and my PhD problem is to actually mathematically model the trajectories of sports balls. So understanding aerodynamics is actually half my thesis work. So on that note, I also integrate Newton's second law to get the trajectory of the ball in air. But as you know, the major problem is here the modeling the drag and lift coefficients, which can be a function of both Reynolds number and spin factor. So you have shown for different sports how CD versus RE graph looks like, but how do we include the spin factor? Because spin obviously plays an effect on drag coefficient, and it has only been empirically modeled now based on experimental data.
Okay, no, that's you're spot on. So spin is very, very important. So we have not been able to do that using experiments. We tried, but there are some difficulties. So we are doing computational modeling. So you can get Magnus effect, you can get reverse Magnus, and even the transition changes. So I have not shown that here, but we are at it. So you could do calculations. They are much easier, I mean, relatively easier than experiments. And on a balance, you can get about 30% variation. So you don't get qualitatively different answers, but you get about 20 to 30% different answers with spin included.
Is it actually possible to mathematically model drag and lift coefficients?
Right. I mean, you calculate it, right? And then you do curve fit so you choose some Reynolds number and some spin rate, and then with that data you could interpolate in between to some reasonable approximation.
Okay, sir. And as you know, both in the experiments and let us say large eddy simulations, we get a time series data for drag and lift coefficients rather than a static value. So is it actually reasonable to just consider the mean value as opposed to the time variations we see?
So you're right. I mean, in fact, I showed some CLCD data. There's some shown here, and these are all time averaged. The question is, how long a time average do you have? So CFD gives you a very small, I mean, because it's so expensive, you cannot do too many vortex shedding cycles. Experiments, on the other hand, will give you a lot of data. So you can take data and see how it changes depending on the time on which you average it. And it turns out you're okay because the vortex shedding frequency is quite large, right? I mean, the Thruwell number will be of the order of 0.2. So you get several vortex shedding cycles during one motion of the ball from one wicket to the other. So I think it's a reasonable assumption to time average. But you can do a moving average if you want. If you want to do an unsteady simulation, which is at every time instant, then it's very expensive. I don't know if you can do it. If you can do that, that's perfect. That would be the right way to do it. But with the computing power available, I think that's too much to ask for right now.
I would like to meet you and discuss more about this subject.
Okay, come on.
I mean, since there are others with questions, right?
Yeah.
Thank you. Sir.
Yeah. Hello, sir. My name is Kirtesh. So I want to ask you, like, are you considering where the ball pitches and how that moves?
Okay, no. That's so. In all this excitement, I forgot to tell you what has been neglected here. Okay. So we are assuming there is no ground. Okay. So the
Okay.
ball is just moving in an infinite domain. So truly
Okay.
speaking, the ground will modify the flow. The spin will modify the flow. Okay. So these are really first cut answers. We have not included the dynamics. So as you will see, when a bowler bowls,
Just a throw.
uh, we are saying the ball holds its seam orientation, which will never happen, especially after bouncing. After bouncing, the ball will do all kinds of things. So we have not looked at that. So these are really zeroth order results, just to kind of understand the basic thing, and then to build on it, you'll have to include all those effects.
And what about the back of hand deliveries? Like that Andrew tie used to do, like.
So that's what I said. The knuckle. So Andrew actually used to bowl knuckle balls. Right.
Or else, like we can say Harshal Patel, like you should do back of length, like in.
So it's So instead of a backspin, you are saying you somehow import forward spin. Is that what you are saying? So instead of
this way,
you will impart forward spin. So that actually would change only the. Okay, so now that you have touched upon that, typically what happens when you backspin the ball, because it has a higher spin on the upper surface, the higher speed, so you will generate more suction, so you get a Magnus spin.
Okay.
So the ball will lift. So if I am a batter and the ball is spinning, it will actually lift. So it's better for me as a batter. What people like Bumrah do is they give so much spin and they are very close to the turbulent transition. So actually you get something called the reverse Magnus effect. So the lower surface becomes turbulent and you get a dip in the ball. And the batsman is thinking the ball will rise, but actually it dips. So Andrew Tye is also able to do that. And I think these bowlers are very difficult because their speed is very large. So by the time you realize it's all over.
Okay.
Yeah, these would be very interesting studies.
Okay. Thank you, sir.
Thank you, sir, for the wonderful talk. So, I have a question regarding in these analysis, the mass distribution was uniform for the ball. So, but in reality, we have when the batsman hits the ball, so the mass distribution is sometimes not remain the uniform. So, how will these analysis vary, and how will it be taken into the consideration?
No, that's a very important point. So you're absolutely right. The CG can shift a little bit, but that doesn't shift too much. The important thing is the shape of the ball changing. So instead of a sphere, it would look very, very strange. In fact, if you notice, the baseball is not really a sphere. It has a very strange, it has an 8 type of a seam. So that's why baseball trajectory is very important. So I've talked to some bowlers and they are able to swing a ball even when the seam is not prominent, even with an old ball. So they will just look at it that how the ball is deformed, and based on that they can swing it. Those studies computationally would be very difficult to do. It would probably be useful to do them experimentally. So you would have to build specimens. Either you have to choose balls which are deformed and do experiments on them, or find a way to 3D print deformed balls. So we have not looked at them, but they are important from a practical point of view. In fact, I once had the privilege to meet Mr. Javagal Srinath, and I asked him that when the match after the toss, whoever wins the toss, they are actually offered about 1.5 or 2 boxes of balls, and the captain can choose any one of the balls. And one would imagine they're all new balls, but they're all different. Even the brand new balls, they're all different. So for example, the captain would take 1 or 2 fast bowlers, and they would roll the ball gently, and then see how it is behaving, and then they would choose the ball. So it's very complicated. Here, I think the idea was just to understand the science of a brand new ball, everything else being very vanilla. What you are saying is now stretch the science even more, which is a good thing. One should look at that. Do it.
Yes. Okay, sir. Thank you, sir.
Yes.
Thank you, sir, for a nice presentation. I have a generalized question like what you did in the experiment. When you hold that shuttlecock in the badminton experiment, that shuttle experiment, does that affect the study? Like when we hit the badminton, that
Excellent.
goes freely.
Excellent. Yeah, again, a question that I should have addressed that, but I had so many other things. So there are two effects of what you are saying. One is the way we have held the shuttlecock, we are not allowing it to spin. If you remember, a shuttlecock, when it is hit, it actually auto-rotates. And that has some impact on the track. In some cases, it increases, in some cases, it decreases. And we are doing those studies now. I have not shown you the data. That is one. The second part of your question is, even if you neglect that, does it have an effect on the flow? Because you're adding a strut to it. So we have done the experiment with a thin one and a thick one, and it turns out it's not very significant.
No change.
It's not very significant.
Sir, one more question like you shown the result of the synthetic shuttle. So, and you have shown that maximum speed is around 500 km per hour.
Correct.
People have
That's
shuttle.
the world. That's the world.
Yeah.
record.
So does the like in the feather shuttle also is it the shape?
It
will
is
be
with the
changed?
feather shuttle. So that
Yes,
speed
sir.
is with the feather shuttle.
So yes, sir. So in the feather shuttle also the shape will change like to the
No,
square.
feather shuttle, it doesn't change much. It doesn't change as much. I don't know what was the shape when it went to 500 kilometers per hour, but we have tested to something like 70 or 80 meters per second, which would be like 300 kilometers per hour. And there's a small reduction in area, maybe about 5% or 10%. So from a digital camera, we can estimate that. But the shape remains very circular. These feathers are very stiff. Okay, so it doesn't change much. But if you take a plastic shuttle, a nylon shuttle, that at that speed it just buckles.
I want last question, generalized question. Sir, why in India there is no manufacturing like for shuttle?
Open a startup. I'll give you free consulting.
No, no, sir. I am asking because we are
Actually, I have
purchasing.
asked this question myself, and it's an open thought for everyone. Um, each box of shuttlecock is about 1,200 rupees.
1400 now, sir.
You take place with 350 or which one?
Yeah, my is 350. It is around 1400.
Yeah, it's about 1400. So we have a regular supply. We get for 1200. Okay, they know these stingy professors. Uh, but I think each shuttlecock is no more than 15 to 20 rupees. Okay, so a box would be calling, maybe 150 rupees at max. There's so much money that one could make in this country. This country would make. So there is a need.
So there is need of research or manufacturing or what? Sir,
Actually,
according to you.
If you remember, I made a remark that these shuttlecocks are very intricate. So somebody who doesn't understand fluid mechanics will not be able to replicate these shuttlecocks. I mean, the features are just amazing. We have figured them out quite a bit. Okay, so if you just take a shuttlecock and just re-engineer it, it will not work. You need to understand some science. Okay, I think so. Some people have. I got some queries from people in Jalandhar. They said they have tried manufacturing, but none of them match up to the real shuttle. Okay, so when I got in touch with them, there's not been a response. But I think that's very important. We should make our own, and we should become exporters. Why not?
I think 100 is a company that is trying, but we should contact them.
Okay, give me the number. I'll contact. Absolutely.
Thank you, sir.
So now I would like to invite Professor Ishwar Prasad from IIT Indore to kindly felicitate Professor Mittal.
Oh, okay. Be separate. I hope there are banknotes inside it of high denomination. I think 2000 is the maximum now. It doesn't seem too much. Thank you.
Moving on to our next plenary talk, we are honored to welcome Professor Kiran Kuchi from IIT Hyderabad. Professor Kiran Kuchi is an esteemed institute professor at the Indian Institute of Technology, Hyderabad. He is also the founder and CEO of YSIG Networks, a Hyderabad-based 5G wireless startup established in 2016. Professor Kuchi completed his MTech and PhD at the University of Texas at Arlington in 1998 and 2006, respectively. With over 100 international patents to his name, Professor Kuchi is widely acknowledged for his significant contributions to communications and signal processing. He has also served as an adjunct professor in the Department of Electrical Engineering at IIT Madras. Currently, Professor Kuchi leads the Government of India funded Indigenous 5G Testbed Program, a US $40 million research initiative involving multiple IITs to develop an end-to-end 5G system. In recognition of his significant contributions to the advancement of telecommunications technology in India, Professor Kuchi was honored with the Pandit Deen Dayal Upadhyay Telecom Excellence Award in 2024. We warmly welcome Professor Kuchi as he takes the stage.
Good afternoon. Very engaging talk by Professor Mitter. I was walking into this room, I saw some equations. I thought, oh, I have to listen to these equations, but somehow he was able to make us appreciate the equations and graphs and enjoy them. Really amazing. I think the Holy Grail is he comes up with some secret mantra that he whispers into maybe Bumrah's ears, and he can start taking more and more wickets. Hopefully, it can happen. Some secrets, at least cricket swing, can be unraveled that are not yet known. I am going to talk about something very different. I've lived a life of an academic all my life, but also at the same time, parallelly, I lived a life of working in a company, starting a company, building a company, developing product. I've done this simultaneously for last 20, 25 years, although I've been in a university system for most of this part. So feel free to ask any questions you may have. You can interrupt me if you wish. So the way I approach my day-to-day work, in everything I do with my research and teaching and also the company I run, the fundamental motivation comes from the current situation where India stands and what is required today and tomorrow and maybe some decades from now. I see so many young people. I think in 20, 30 years, you'll probably see hopefully a more developed India. But at the same time, the country is going through a rapid transformation and transition to knowledge-based economy. I think we all know what it means. And this has two parts. One is a pure knowledge-based society, dealing with software systems, things like that. Then there is this hard manufacturing based system. I think we're talking about why can't we create these shuttlecocks, although professor knows so much of the science, yet we are not making something as a shuttlecock. We're all buying it. So this manufacturing based economy is something that's going to emerge, I think, all indications point towards that. I think there is no doubt that science and deep science and engineering is the only path to our progress. You know, there's no other substitute for deep tech. I mean, look at every other country, advanced and developed country. I mean, you see what's happening. So, uh, Silicon Valley is an amazing place. I keep going there very often for various reasons. I go through first East Coast and then I go to West Coast of the United States, and there is a striking difference between these two coasts. Um, I interact with a lot of people in the West Coast, and it's an amazing place. I think most of the global wealth uh, is controlled by some 6 or 7 companies centered around the San Jose, San Francisco, what is it called, Bay Area, okay, around the Bay. And I mean, I don't have to state the obvious. Several PhD students, those who completed their degree, those who didn't complete their degree, they converted their brilliant ideas into nearly $1 trillion companies. Okay, so there is some inspiration to be drawn what deep tech and science can do. Okay, so I mean, looking at all these young people here, possibly, one or two of you, may end up creating $1 billion or a multi-billion-dollar venture, maybe 20 years from now, who knows, you know. It's quite possible. I think it should be done. I think it's time, for India to step up. On the other hand, China, when they started delivering these copycat companies, and firsthand, and you look at it, oh, they're all copycats. But you have to study these copycats. They're not just copycats. There is a lot of deep science and engineering behind these copycats. So it's interesting to study these the other our neighbor, how they have transformed deep science and technology into a country that's now possibly challenging their status quo. Okay. Uh, so the first part of my message is that there is so much room for deep tech and science, and I think that many of you, if you stay focused, it's going to take several decades. It's not going to be very easy, but it's going to be several decades, and but it can be done. Okay, so I'll talk about the company I built based on some of these principles. Will showcase you something that really works, that's being commercialized. Before that, for PhDs and those who are venturing into deeper aspects of your research, I've seen that the professor has shown a lot of science, and then he has done some measurements, and then there's a very good match. At least in electrical engineering and wireless communications, the field I practice, there's only so much you can do writing down the equations. There is only so much you can do doing computer simulations. There is only so much you can do building prototypes of systems. Actually, you need to have a very unique combination of all these three skills if you have to make a very deep impact. Now, especially those who build super cutting edge products, many different sets of skills comes into picture. You need to know the science, you need to know the engineering, and you have to actually build and toil with it quite a bit. I can go over some examples of that with the products that we developed. Then there is this other part. The students and professors are rewarded, for 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 writing papers with very good science, mathematics, that are here, well cited. This is where you gain respect. Okay, but in this process, uh, don't neglect sometimes incremental innovations. Incremental innovations sometimes are not rewarded from an academic point of view, but in practice, incremental innovations can make a very large difference. Okay, one example is there is this GPT, and then there is this the Chinese version. The Chinese version is actually an incremental innovation, but the impact that has created is just so profound. It is still deep tech. Okay, this is the fundamental difference. And the GPT has so much deep science and so many billions of dollars of money that's put into it. And people thought that it's nearly impossible to create an equivalent version, but somebody has shown that with a fraction of that money and with some moderate amount of deep science, they could create a similar product. So never underestimate the power of incremental innovations, especially a second mover. A first mover, being a first mover is very, very difficult, but there is a second mover advantage. So always keep this in the back of your mind, and you can still make a very, very big difference being a second mover in any field you take it. But still, it takes deep science. But maybe you can get things done with a fraction of the efforts that the first mover has put in. Okay. So as a researcher, always you have to play to your strength. This is true in sports. This is true everywhere. I think we have to understand ourselves and play to our strengths. Then results don't come in very easily. It takes decades and decades of hard work and persistence. I think any professor will tell you for a very, 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 very long haul. So I will show something that we have created uh, based on some of these principles I've been talking about. This picture that shows here is a 5G communication system built in this campus. Research done here, decades of work done here since the foundation of this university, this IIT, and done in a in a venture that we created a company. And if you tell somebody that this is done at probably at tenth of the cost of what the first mover has done, those who have deployed 5G, you'll be very, very surprised. But this is a system that works. It is developed 100% here in a very unique manner. This is a site that you can see just in the adjacent building it is deployed. It's a 5G network end to end. So I'll show you some interesting results of this 5G that is developed here. There are about 100 people who worked on this, and the average age of this team is less than 25. And there are maybe 10 people who studied here with me for over 7-8 years. They've been with me. They joined this venture. Then there are engineers who were trained here for several years before we absorbed them into the company, and they worked in various research projects. Every engineer that worked in this project has been created more or less here. We didn't have people coming from other companies with past experience building the system. It's developed from scratch. Okay. So we built this system. I'll give you a kind of view of what it does. This is IIT Hyderabad map. So just around the campus, adjacent to the campus, there is a lake. I mean, if you climb on this building, you can see it. Around the lake, there is this village called Chimnapur. We put a 5G site here on top of a house. Okay. This technology includes antennas, radio wave propagation, chipsets, signal processing, communication, protocols, whatnot. Okay, it's a mega system. It communicates with the cell phone, right? The one I hold in my hand. these phones connect to the system and you can get internet connectivity. This is the classical 5G system that you see offered to you, by service providers. So this is everything is in these boxes. Okay, a lot of electronics, chipsets, but our play is systems and software. So we put this system in this village at this dot, and we covered the whole village using a new concept called fixed wireless access. So when you take the system to, let us say, a rural area, not everyone may have access to a 5G phone. So what we have done is we put this box on the electricity poles. This box is kind of like a 5G cell phone, but more like a fixed unit. And a few electricity poles in around the village, we put this box, and it connects to the 5G station, 5G cell tower. Then this can translate these signals into Wi-Fi, and people around the homes and the nearby 5, 6 homes or 10 homes can connect to through Wi-Fi. So this school right here is connected through 5G network, through Wi-Fi, through this intermediate node. So we solved one what is called a societal problem here, because in rural areas people don't have 5G devices. Now any device which is Wi-Fi enabled can have 5G experience through this transformative node. Okay, so with this framework, we went around the village and we started taking measurements, different parts of the village. So in almost all places, 165 here stands for 165 megabits per second, and 65 to 75 stands for 65 megabits per. This is a lot of speed, by the way. Many people can share it. Either people holding handsets, whether it's 5G or not, or televisions, or laptops, desktops. There is an Anganwadi there. There is a school. There is a ration shop. We offered this connectivity to several people as an experiment. So people are connected. Then this is one village. And we went to the adjacent village, which is about a kilometer away. And on the ground of the village, the signal didn't reach because this site has a limited reach. This particular site. And what we did was we climbed the roof of a house, and you start getting the signal. So we just put an antenna up and then started offering connectivity. So in summary, the invention here is, of course, it's a commercial invention. The entire 5G radio access network has been developed here, and it's done with less than $30 million budget. I mean, if the same has to be done elsewhere, it will be around $300 million. Okay. These are people who came here 10 years ago, 5 years ago, with almost no background in this field. They've been trained. Most of them are self-taught, and this has been cracked. And this is we're going to roll this out nationwide and elsewhere, in other parts of the world. So what we're trying to say here is that it is possible to translate ideas and inventions and academic research into real life products. Okay, this is one example of that. It's possible and it's done. Okay, and the path to achieving this kind, of course, this is a very complex project. I don't necessarily advocate everyone to take this kind of a path, but the paths are never defined anyway. Everyone's path is different. I can't say what any one of you could possibly be doing 20 years or 30 years from now. But it is indeed possible that the deep tech can be commercialized into deep tech products. This is a statement we would like to make. And path to doing that is highly non-obvious. In this particular case, it is done through an university-led system. Of course, a lot of government funding, hundreds of crores, have been put into this before we even started this effort. Several hundred crores of public funding went into this kind of effort before this background has led to the creation of a company. Of course, the company does this in a private and for profit mode. So this is one of the cool examples of what public funding can achieve. Of course, sustained over a long period of time. The seeds of this were sown when we were in the ordnance factory, literally in shacks. We didn't have anything back then. We were building the IIT Hyderabad system, and that's when the seeds of this kind of tree were sown. We have developed over 200 patents. Many are essential to implementation of 5G technology, including the phones that you carry, include protocols and waveforms and innovations that we patented and introduced in the global standards. That's a talk for another day. They're included in these patents. These patents that have been commercialized. And using these patents, we've been able to develop highly differentiated products. There are products and then there are differentiated products. There is something unique that you have to offer if you have to compete with incumbent. We're talking about this shuttlecock, and you can build a Me Too shuttlecock, and then maybe there is a secret that can give you, that can give you a differentiation, right? So building differentiated products requires deep science and technology. So we had the uniqueness of hiring people. 80% of the people who work in this company that we incubated, although I'm a professor here, they come from rural areas. They don't come from IITs. They don't have a degree in IIT. 80% of them. 20% of them are women. About 10% of them probably have some kind of IIT background, a PhD or an MTech. A few have a BTech in IIT. So you will be amazed what people can do, but provided have to sustain it. People have stuck with this kind of an effort and a venture for a long period of time before we started seeing results. They did it because they enjoyed it, and they had the hunger, and they've been trained here in that kind of an environment. So with this, I would like to conclude my message. Good luck to all of you, those who are venturing into research. I'm sure you will succeed in whatever subject you are trying to study. Thank you.
Yes, sir, for your insightful talk. Now the stage is open to audience for some questions.
Hello, sir. So I'm wondering where most of the budget goes. Is it into the certifications or salaries of the employees, or to build prototypes which might fail again and again? I'm just curious of the proportion of the budget, how it generally works in R&D.
See, every field is different. In let us say, in this particular product that we develop, it's called a 5G network and a base station. In this product, a disproportionate amount of money initially goes into manpower. Okay? And manpower is becoming very, very expensive in India for whatever reasons. Of course, the second one is the technology that we use in these products is very advanced. There are chipsets, there is design, there is manufacturing. That's the second part. But as the technology readiness level keeps increasing, initially it's the manpower. But as you go towards production grade, then it is the equipment and the as technology readiness level, TRL. As you move towards 7, 8, and 9, then the proportion of money you have to spend for mass rollout, the equipment and other things will take over. Certification, they'll take over. Initially, it's the manpower. But this is for this particular product. If you're designing a chip, then again, same story. We built a chip, by the way, I didn't talk about it in this. We built a very complicated 5G class of chip that has immense what do you call IPs and design IP and manufacturing component. One tape out would cost you $5 million if you use a very advanced semiconductor node. So every field is different. Yeah, but don't underestimate the manpower cost. That's incredibly high these days.
So since the private companies run basically on profit, so does a consideration of number of years it takes for recovery also go, gets into the picture, or
Of course. So this company has been in existence for 7 years, more than 7 years, but it has sustained itself through its own revenues. There was a unique model built into it, then through public and private funding. Yeah.
thank you.
So I have different, wonderful presentation. By the way. So I think there are certain misconceptions in the village people that if you're actually putting a network, 5G network, there is some kind of radiation effects. So did you find any backlash from people, at least certain kind of people, when you go this proposal that you want to install some kind of 5G network in your houses or something like that?
Yeah, this is a very general question. So let me see the tower that I. No, there are many towers you see around the campus. So this is an antenna. This tower radiates, let's say, 200 watts. Okay. So those who know electromagnetics, simple physics, if you radiate 200 watts from a point source, the wave goes as a spherical wavefront, and within 100 meters, the energy per square inch becomes negligibly small. And as it goes further and further, even within a few, let's say, maybe 15, 20 meters, and if you're putting here and you're exposed somewhere here, the energy that you receive from the spherical wavefront is abysmally small. So the only thing you have to watch out for is that if the antenna is close to, let us say, your window and it's within, let us say, a few feet, then you are in the near field. That's number one. Number two, the heat is an issue. So the heat generated here is an issue. That's why there are regulations that within maybe 10 to 15 meters of this antenna, you can't really have anything around that. Other than that, the energy that you receive from the phone, right from the 2G, is probably a million times higher than what you'll receive from this tower. Just to draw a comparison, because it is so close. Yeah. I'll leave it at that.
Now I would welcome Professor Sunetra Sarkar to kindly come up to the stage to felicitate Professor Kuchi.
Sorry, I was going to. Sorry. So please come here. Come in the middle of the stage. So I just want to take this opportunity to formally thank you on behalf of IIT Hyderabad, presentation team, and the coordination team. This is a wonderfully organized event, and we are a very great and fantastic sorry. Yeah. I have a loud voice. Okay, so this is from IIT Madras. Thank you so much. Yeah. Thank you. And yeah, thank you. Thank you.
Now we will have a short break for the poster sessions and refreshments. We will reconvene at 4:45 p.m. for the next set of plenary talks. Welcome back, everyone. We will be having the pre-final plenary talk of the day now. It is our pleasure to introduce Professor Rajalakshmi from IIT Hyderabad. Professor P. Rajalakshmi is an institute professor at the Indian Institute of Technology, Hyderabad, holding the Science Chair Professorship in Future Communications. She is also the director of the NMI CPS Tihan Foundation at IIT Hyderabad. She completed her PhD in electrical engineering in 2009 from IIT Madras. Her research focuses on autonomous navigation technologies, wireless sensor networks, and smart transportation. She was awarded the Vishwesvaraya Young Faculty Research Fellowship under the Vishwesvaraya PhD scheme for electronics and IT from DIIT in January 2016 for a 5-year tenure. In 2016, she also received the Digital Trailblazer Award from India Today. In 2014, Professor Rajalakshmi was honored as India's most inspiring women engineer and scientist by Engineering Watch. Let's welcome Professor Rajalakshmi onto the dais.
Yeah. Good afternoon, all. I think today I'll be briefly talking about the autonomous navigation technologies or the research that we are conducting at IIT Hyderabad. Yeah. So, just to briefly say, this project have been. Am I audible? If I'm standing here. Okay. So basically, this project, it is funded by Department of Science and Technology to IIT Hyderabad. Where Yeah, so here what we are doing is we are working on, I would say safe, sustainable, next generation mobility technology. Okay, so when I say next generation mobility technology, we are talking about end to end, mobility. When I talk about end to end mobility systems, it starts from something which is listed here. Starting from sensors, quality data acquisition, okay, then fusion, multiple sensor fusion technologies, okay, then coming up with perception. When I say perception, here, how the sensors perceive the environment, okay, after which comes the AI/ML part of it, because we are talking about autonomous, okay, when it is autonomous, there is no human intervention. That's where, we come up with artificial intelligence, machine learning techniques integrated into the system, okay, and then the most important, actuators or the control algorithms, okay, so that's where, the path planning control algorithms also play a very critical, crucial part or the subsystem of the complete end-to-end navigation stack, okay, and going forward, I would also say that there is a huge focus on computing, particularly real time. Okay, because we are talking about autonomous systems which are going to take on the fly decision making. Okay, so it is going to be kind of real time edge compute, how to integrate real time edge compute into the system, where most of the intelligence heavy computes can also be offloaded into kind of fog or edge clouds architectures. Okay, then communication and networking part, again this is most important. This enables, vehicle to vehicle or vehicle to drone, drone to drone, that kind of communications, okay, not only between the vehicles, it also enables communication with the ground control station. Okay, so how the communication architecture is established. Okay, so these are all the key, I would say, fundamental subdomains which are involved in the complete end-to-end, autonomous vehicle development or autonomous drone development. Most important next thing is testing and validation. Okay, so when we are talking about the complete end-to-end system development, how do we go about, testing and validating the systems? Okay, there are multiple ways of doing it. Like software-based simulation, emulator based simulation, hardware in loop kind of thing, and then proving grounds, where you actually come up with tracks or the airspace in which the system is deployed and the different kind of validations are done. And the most important thing, there exist standards. When I say standards, it can be ISO standard or UNEC standards, or for that matter, it can be also airspace standards. Whatever DGCA standards, BIC, VIS standards, or for communication, different kind of IEEE standards. Okay, so there are standards defined. Okay, which gives us some what was it guidelines for testing and validating the product that are being developed. Okay, so this is the most important thing when we are talking about product development at higher TRL levels. TRL level is nothing but the technology readiness levels. So anything beyond 7 is something which is ready to go for commercialization, right? So testing validation helps define the TRL level of a product that is being developed. Okay, and then simulators, as I was saying, they was one is virtual simulators. Virtual simulators are nothing but your system based simulator. When I say system based, it's all the simulations. And physical simulators, that is where virtual loop, vehicle in loop or hardware in loop or proving grounds, those kind of things come into picture. Okay, and the most important, the next important aspect is the design aspect, which is again the most I'm also seeing some of our design PhD guys here. The how do you design the vehicle, the next generation vehicles. We know the current design aspect, but now um, I think the Gen AI, right? Most of your design tools now come with also your Gen AI integrated. Otherwise, earlier for design, first you come up with the design, do the different, simulation, analytical simulations on the design parameters, and then check for the, airworthiness and other stuffs. Okay, in the simulation aspect. Now, with Gen AI integrated, you can come up with different designs, and it actually reduces the product developmental life cycle. Okay, so that way, design aspect also plays a very, very important role when you actually talk about the end-to-end system development when it comes to autonomous navigation or autonomous vehicle, autonomous drones, whatever it is. Okay, so this are the main subdomains which is involved in the development of the complete end-to-end stack. Okay, now, coming to IIT Hyderabad on autonomous navigation, mainly on research and development. The next very important thing, we also support innovation in terms of startups. That's what is listed here. Okay, so a number of startups in this area is also being supported by IIT Hyderabad under the HAN project. Okay, in the area of mobility, and a number of fellowships again starting from undergraduate, I would say BTech internship, PG fellowships to PhD, postdoctoral, and faculty fellowships, chair professorship. Different kind of fellowships are also being supported at IITH in the area of mobility. Okay, under this project. Okay, so let's get into more details about the technicality. Okay, about at least broadly, I will say what are being covered in this project are being carried out actively. So as I was saying, these are the subdomains. System, sensor control, communication, networking, AI, ML. Okay, real-time edge compute, design aspects, security aspects. Okay, simulator, safety, testing, validation. The most important, as I was saying, the commercialization aspect. Okay, commercialization, it can be through TOTs to the industries or to TOT. When I say TOT, that is you develop the technology and invite partners to transfer the technology on a licensing basis or a royalty basis, whatever it is. And the other way is you support the startup who can take the technology. Okay, that is the entrepreneurship, management, business studies aspect of it. Okay, now going forward, so as I was saying, like at IIT Hyderabad, this is very unique in terms of mobility research. We have come up. So this is our campus. Okay? It's around 600 acres. Now almost like 10 acres of land we have created as a test bed. When I say test bed, we have the track. Track is nothing but this kind of tracks. We have the 2-lane road, 3-lane road, different kind of junctions, and etc. This we call as a test bed or the living lab, where after a POC is being developed in the lab, It can go for real field testing. Okay, so when we say testing, we can do even high speed testing at 70 km per hour, 80 km per hour. Autonomous vehicle testing can be done in this test track itself. Okay, so that is one of the very unique thing in the country itself, where an academic institute have a proving ground to test an autonomous vehicle. Okay, so this is very unique about IIT Hyderabad, the first of its kind autonomous navigation test bed is developed at IIT Hyderabad in an area of around 10 acres. It not only supports ground vehicle research, but also it supports drones. When I say drones, we have hangar facility and different kind of wind shaper, kind of different kind of gust conditions can be created, which can be useful for testing the vehicles for different wind conditions and things like that. So it's a very unique facility. That's what is written here. Test tracks, hangar facility, ground control station. Then you have smart poles. When I say smart poles, it has different kind of sensors integrated to it. Multiple radio is supported. When I say multiple radio, it starts from Wi-Fi, beyond visual line of sight, 5G, different kind of radio technologies are also integrated. Okay, so it's very unique in terms of the facilities that exist in IIT Hyderabad. Okay, so when I say this is again one of the very unique thing, rainfall simulator. So it's like a big structure in which different intensity of rain can be simulated or emulated, and the vehicle or the drone can be tested for different rainfall conditions as well. Okay, yeah. So going forward, let me just go to this part first. Yeah. So what do we do? Okay, as autonomous navigation, technology. So as autonomous navigation technology, we come up with this end-to-end autonomous driving stack development. Okay, so when I say driving stack development, okay, so there is going to be multiple sensors. Okay, when I hope all of you know some of these sensors like camera, lidars, radars, right? So these are some of the sensors which are being utilized in most of the autonomous systems or in robotics applications. Okay, and GPS, GNSS systems for positioning purposes. Okay, and you have IMU and other stuffs as well. So primarily different kind of sensors, starting from GNSS, which is a 1D data, to radar, 4D radar data. Okay, I hope you have seen also nowadays the point cloud data from LiDAR, which is a three-dimensional data. Okay, so depending upon the type of the application, different sensors can be utilized for the application development. Okay, so different kind of sensors are being utilized and can be fused depending on the requirement. Okay, so more and more sensors you add, the system becomes more complex, but it becomes more robust as well. Okay, so that's where people talk about when you talk about Tesla, it is multiple sensors in the sense multiple camera mounted all around the 360-degree coverage of the vehicle. Okay, so that the reliability is more enhanced. So kind of multiple sensors, fusing them is one of the very important thing if you want to actually enhance the robustness of the technology. Okay, so this is the first thing, sensor, multiple sensor fusion technology. Then comes your perception. So when I say perception, it can be anything starting from lane detection, okay, traffic light detection, traffic sign detection, object detection, another car detection, whatever it is. Okay, so you need to perceive the environment. Okay, so that is a perception stack development. Okay, then following which you are going to have the path planning. So when I say path planning, okay, what do I mean by path planning? Path planning is nothing but can be global path planning and also local path planning. Okay, global path planning is coming up with the trajectory between the source and the destination, and local path planning refers to identifying an alternative path whenever there is going to be some obstacle in the path that have been predefined. Okay, so such kind of algorithms exist. Okay, path planning, the simplest path planning is your shortest path routing, the Dijkstra's algorithm, right? So this kind of path planning, then comes your drive by wire. What is drive by wire? It is nothing but the control algorithm. Okay, that is when I say control algorithm, whether I need to stop the vehicle, whether I need to accelerate the vehicle, whether I need to turn the vehicle, steering. Okay, so you have basically 3-wire or 4-wire, drive-by-wire mechanisms when it is like, acceleration, brake, steering, and reverse. So these are different, steering or I would say control drive-by-wire mechanisms that are being adopted for controlling the vehicle. Okay, so this complete thing, starting from sensor fusion, perception, path planning, and generating the control algorithm to control the vehicle, forms a complete autonomous driving stack. Okay, so at IIT Hyderabad, we have this complete in-house autonomous driving stack developed. Okay, and when I show these different kind of vehicles, we have this autonomous driving stack developed, designed and developed for different category of vehicles. When I say different category of vehicles, these are golf carts. Most of you know this. They are all slow moving vehicle, which goes up to 20 km per hour, or some of them go up 25 km per hour. Okay, this does not require any registration from the ARAI or ICAT kind of organizations. While other vehicles, which are commercial M1 category vehicles, they are all like higher speed vehicles like 120 km per hour or 150 km per hour. Okay, so the driving stack, okay, changes with the type of the vehicle, the dynamics of the vehicle, the speed of the vehicle. Okay, so this stack gets fine tuned according to the vehicle in which we are developing and which we are actually deploying the technology. Okay, so this is what is the autonomous navigation technology research that is being conducted at IIT Hyderabad. Okay, we do the sensor fusion, we do the path planning, we do the control mechanism. Okay, and deploy it in different category of vehicle, and the complete stack is ready. Okay, so this is the basic. Okay, now going forward, in this, if you see, mostly here, in the perception, right, it is where the more, more kind of data is involved in, whatever camera kind of data or LiDAR data is required to come up with robust stack development. When I say robust stack development, it may be detection algorithm, it may be YOLO V11, it may be YOLO V5, V6, V7, whatever. Okay, kind of different kind of algorithms that are being used requires a huge amount of data being collected. So when we talk about the data being collected, that is where this is becomes very important. Okay, so we have a vehicle in which we mount different kind of sensors. Starting from this way, you can see this is a 128 lidar. Okay, and we have different kind of cameras which provide 360-degree view, and this is a radar. Okay, and we have different kind of radars also mounted around the vehicle. Okay, which will provide again 360-degree view. Okay, so this data collection vehicle, again very unique in the Indian setup, where it goes around in the roads, or not to, we have collected huge amount of data in the Hyderabad city, around 3,000 kilometers of data, and recently we have sent the same data collection vehicle, okay, to from Hyderabad up to Jammu. Okay, one way going around 3,000 plus kilometers, around 7,000 kilometers of data, where we spend different city time in different city collecting data. Okay, so this is very important. Okay, so when I say data is very important, you see this, right? This is your camera. Okay, camera and lidar projected, and radar and camera projected. Okay, so different kind of projections on the collected data can be done. Okay, and this kind of diverse data set from different states, help recognize different kind of OCR technologies. What is OCR? OCR is optical character recognition, right? So now I have, a signboard written in not only Telugu but also in Gujarati, in whatever, Punjabi and other languages as well. Okay, now I'll be coming up with, training with multiple languages, signboards. Okay, that way a huge amount of data is collected by IIT Hyderabad itself. Okay, and a repository is created, which is useful for creating a robust stack in terms of perception. Okay, And most of you know, whoever is working in AI, labeling or annotation of the data is a very humongous task, right? So most of the times, as I was saying, we have collected now around 10,000 kilometers of data. So for how do we do the annotation? Generally, manual annotation is done. We have also come up with automated annotation tools, right? So the collected data can be given to the automated annotation tool, after which, it creates the required bounding boxes or the classifications, right? And this kind of tool aid, again, I would say, the robust stack development. So this is what is the automated annotation tool or the labeling tool. Okay, yeah. So now we talked about sensor fusion, the perception stack, data collection requirement, okay, that is required for this activity. And now going to the drive-by-wire, again, as I was saying, four-wire steering, four-wire control mechanism. So this is again completely in-house designed and developed. This is being utilized in the campus shuttle, in the campus. I think I will just play this video, at least the autonomous campus shuttle, where this complete end-to-end stack was deployed. Okay, and it is actually from August 2023. Six-seater vehicle, fully autonomous, is flying from the main gate to the, um, our hostel circle, which is around 3.2 kilometers, and it is using the same lane as that of the others. And you can see it is perceiving the environment. Whenever it sees an obstacle, it stops. Okay, and if it, with a safe distance, it follows the vehicle as well. Okay, so this way, the complete stack have been deployed in the campus also for the last 2 years, almost 2 years, where 7 kilometer round trip track service is being rendered. Okay, so what is this? So we know of group of autonomous group of drones. Now this is called as a platooning. Okay, what is platooning? Platooning, it is very important in cases of mining industry, where this is a predefined path, group of vehicles doing the same task again and again. Okay, so this you can see, group of autonomous vehicles, going in a predefined path. Okay, from source to the destination. Okay, carrying whatever it is. So this is again an interesting technology. Okay, so as I was saying, the traffic light and traffic sign recognition. So you can see in the Indian context, each of the country has its own standards. In India, we follow something called as Indian Road Congress, IRC standards. Okay, so all the signs that are being deployed, okay, has to follow the Indian Road Congress. Okay, so again, going across the country, collecting this data is very useful for traffic light detection, traffic sign detection. And what do you think is the most important challenge in this? Recognition in all light conditions, in all weather conditions, right? And if it is in the occluded conditions, right? All these are actually the biggest challenge. So we have to curate the data or train the model, okay, for this kind of scenarios. That is where, huge data collection plays a very important role. Okay. Now coming, these are all about the on-road vehicles. Okay, while autonomous vehicles also have a lot of use case in off-road scenarios. When I say off-road scenarios, it can be agriculture kind of applications, as I was saying, mining kind of applications, warehouse kind of applications. Okay, so that is where we are going to have this kind of vehicles which are called as a varaha. Okay, and this this is one of the startups, again supported by Tihan in the area of autonomous mobile robots. This, if you see, it is more useful for carrying the payload from one location to another in a warehouse kind of scenario. Okay. Yeah. So moving forward, so now we have been talking about intelligence embedded on the vehicle itself, right? So vehicle have the camera, it does all the processing, takes a decision by itself. Okay, more and more you integrate sensors, more and more you do compute on the vehicle itself, it's going to drain away the power. Okay, So in order to make the vehicle, okay, lightweight in terms of compute, okay, the other option is to offload the data into the cloud. Okay, that is where we have this edge cloud and 5G setup. Okay, here we are talking about 5G, while we can also talk about Wi-Fi kind of network. Okay, depending upon the bandwidth requirement. Okay, depending upon the type of the data that is going to be offloaded into the cloud. Okay, you choose the radio network. Okay, so that is what it is. So this is something which enables, moving towards, dynamic platforms. Okay, earlier automotive was supposed to be a static platform. What do I mean by static platform? Okay, so once the manufacturer sends the vehicle to us, all the features are once for all embedded in it, and it is frozen, right? It does not undergo any further revisions after selling. Once the vehicle comes to me, the features are all fixed. Okay, whereas with 5G and edge cloud, or I would say communication and edge cloud integrated into the vehicle, the platform can be made more dynamic. Okay, what do I mean by dynamic? The features on the vehicle can be upgraded. Like it's similar to your, mobile phone. Suddenly you say, okay, your Samsung mobile phone have to be upgraded, right? Update the software, right? Similarly is the feature that is going to be embedded in your automotive also, where the feature in the vehicle can be upgraded, okay, by enabling this cloud or edge, I would say edge based or cloud based services integrated into the cloud. So this in, in turn is what is called as the software defined vehicles. Okay, software defined vehicles are nothing but software is going to define the vehicle features, and the software is what? Software is going to be from the cloud. It is going to be, the features are going to be upgraded constantly, into the vehicle. The vehicle need not go back to the OEM, or you need not purchase a new vehicle if you want to have new feature integrated into your vehicle. Okay, that is what is called as the software defined vehicle. This is one of the future mobility concept. Again, how people, where the mobility is moving towards. Okay, yeah. Yeah, so this is briefly about the ground vehicles. Now let us talk, a few words about the drones also. Drones also. Again here, as you can see, different category of drones are being designed and developed. Okay, when I say different category, you can see this is something called as ornithocopters or bio-inspired drones. Okay, so where these are, I would say at a very nascent state of research. Okay, why? Because again, the payload carrying capacity, the structural stability are still under a lot of research is going on in enhancing the endurance and the structural stability. Okay, so this research is also being carried out. And while the other conventional kind of drones, other that is like it can be like a multicopter. Okay, it can be quadcopter, hexacopter, whatever. Okay, of different payload capacity is also being developed. Again, in this case, the autonomous flight stack. Okay, when I say flight stack, you have the same architecture, starting from multiple sensor fusion, again perception, again here fly by wire. Okay, in the case of ground vehicles, we had the drive by wire technology. In this case, we will have the fly by wire technology, which will make the complete autonomous drones. Okay, so that is what is being followed. So these are some of the use cases where in this case you can see around 27 drones, okay, being, swarmed in the air. And most of us know around 5,000 plus drones are being utilized now for what? Drone show applications, right? For entertainment purposes, following, forming patterns in the air. This particular thing, it is useful for large area surveillance. Here the objective is not forming patterns in the air. Okay, whereas this is, you distribute group of drones in different directions in different areas. Okay, so that large area surveillance can be done. Okay, that is the application. And here again we have utilized, centralized different kind of swarm or network concepts, like, centralized and distributed concepts. Okay, you can go through this again about the swarm technology. Okay. The next interesting thing is, beyond visual line of sight. So what is this beyond visual line of sight? I mean, as of now, DGCA has regulated drone operation only for visual line of sight. That means like I'll be able to operate the drone only as long as it is visible for the pilot. Okay, I'm not allowed to operate beyond visual line of sight, beyond the sight of the pilot. Whereas this one is beyond visual line of sight. That is, the drone can operate from the ground control station to any distance. It can be 5 kilometer away or 10 kilometer away, 25 kilometer away. Okay, so that is visual line of sight technology, and it is very, very useful in case of what, in case of drug delivery, cargo delivery kind of applications. Okay, so that's where here, we are actually showing a drug delivery application where, from our hospital, which is around 2 kilometer away from the Tihan test bed. Okay, the sister has, placed some medicine, and this drone has gone and delivered the medicine in the test bed, which is around 2 kilometer away, which is again the beyond visual line of sight. Okay, special radios are existing for this purpose, which is around 900 megahertz, which is utilized. And from IIT Hyderabad campus, around 10 kilometer radius can be monitored with this radio. Okay, so that is very, very important. We have tested from IIT Hyderabad campus up to 7 kilometer radius, up to 7 kilometer distance range. This beyond visual line of sight technology. Yeah. And the next very interesting technology is GPS denied. Okay. So whenever we are going to do the navigation, as I was saying, position is a very, very important thing. Okay. And at this point of time, position comes from the GNSS or the GPS. Okay. In scenarios like tunnels, okay, or in scenarios where, indoor applications, you do not have GPS. Okay, in such kind of scenarios, you need to do the sensor fusion technology. When I say sensor fusion, it can be camera based, it can be lidar based, it can be radar based, whatever be the sensors, it can be utilized by the IMU integrated on the drone. Okay, and positioning and navigation can be enabled. Okay, so that is what you see in this. So there is an indoor drone, okay, which can navigate with whatever we have shown is a camera-based technology. A SLAM technology is being utilized for navigation inside the hangar facility. Okay, and as I was saying, this is a bio-inspired. This is a honeybee structure, but this is again, as I was saying, it's not robust like the other ones which I showed. It's in a very nascent state. When I say nascent state, I would say this at a tier level or 2 or 3 only. Okay. The most important next thing, the heavy payload drones. The heavy payload drones, anything above 25 kg, it is up to 50 is medium, above 50 is heavy payload. So IIT Hyderabad, we work on heavy payload drones where, we have working prototypes. Okay. So this
24 meters.
itself. Yeah. So these are again different kind of applications on a drone. This is a thermal imager on the drone, which is useful for surveillance applications. Okay. So this is briefly about what we do on drones. Starting from small category drone to heavy payload drone, where a heavy payload drone for higher applications like air ambulances can be utilized. Okay, and testing is going on, and we'll be very successful in demonstrating that as well. Okay, and these are some of the contributions in terms of standardizations and regulations. We participate in different kind of forums like ARAI and other kind of forums where regulation, we also contribute to regulatory or policy frameworks to the government of India. Okay. Yeah. So secure end-to-end connectivity, multimodal transportation, okay, where we work on last mile or the first mile connectivity like slow moving vehicles like e-bikes, shared shuttle services to intercity connect through personalized air vehicles, okay, which actually ensures end-to-end connectivity. this is broadly the end-to-end connectivity or autonomous navigation technology that we work on. Yeah, thank you so much. Are there any questions?
Thank you so much, ma'am, for that inspiring talk. As we are running short of time, there won't be any Q&A sessions. However, if you have any questions, you can reach out to Professor Rajlakshmi. Thank you, ma'am. Now we will call upon stage Professor Iswara Prasad from IIT Indore to kindly felicitate Professor Rajlakshmi. Now, I would like to call our Honorable Director, Sir, Professor B.S. Murthy, to come up on the stage. And I would also like to call Professor Kishalay Mitra, FIC PMRF, IIT Hyderabad, to please felicitate Professor B.S. Murthy.
Hosts are never felicitated. So I'm a host here. Please. Thank you very much. Friends, okay, so tired? You see, one lady is nodding her head. I can see, yes. Research is one which should be so exciting that we should not be tired. Hmm. Abdul Kalam sir used to say, dreams should be all colorful and as colorful as possible. And dreams should be such that they don't make you sleep. Okay? I think as PMRF students, in principle, we should have such dreams which will not make us feel sleepy. That's, I think, minimum requirement, I would say. I always say for a regular PhD student, which should apply for even PMRF student, I'll not take more than 10 minutes, friends. Okay, I did not bring any PPT, so be happy. uh, 10 minutes, I just wanted to tell you a kind of a parting remarks at the end of this particular event. I wanted to spend a lot of time with you, but I could not get time. Please excuse me. These are all professional hazards of my seat. In fact, Pradeep came. I could not even meet Pradeep. So we both used to share an office in the same floor. We both in HSB. Anybody from IIT Madras here? Okay, so HSB, you know. So HSB ground floor, my office and his office are just two offices away. So very close friend of mine. But I could not meet him today. I mean, he must be really cursing what has happened to this guy. What happened to the researcher in this guy? He would have possibly thought about it. But anyway, my research happens only in the night. Okay, so it starts at 8:30. My group at IIT Madras, if some of you possibly know, at 11 o'clock in the night, we go for a cup of tea. I have always had at least 10 PhD students with me. 11 in the night, we go for a cup of tea up to 12, and then come back to the lab. And we don't know when we go. In fact, long back when a very young faculty, joined IIT Madras, my department, his wife asked my wife, "What time does your husband come back to home?" She says, "I don't know." Because she will not need to know because I have the key of the house. Okay, I don't need to wake her up to enter into the house. I sneak in whenever I want, and that's how I lived my life. In fact, very recently on 28th of you know February, when this inventive was happening at IIT Madras. So 27th night, I reached, and I was entering into the campus at 11:30 in the night. Just wanted to take a chance because one of my PhD student was doing a postdoc. He is doing a postdoc, and just called him. Uh, so, Soumya, are you there? He said, yes, sir. So, shall we meet at the coffee place? So, straight from the airport, I went to the coffee place where we used to regularly, next to the girls' hostels, there is Ramu's canteen, we used to call it. I don't know what is the name of it now. So, again, 11:30 to 12:30, we had a nice round of tea and then enjoy. And that gave me so much of energy and brought so many memories of 15 years that I have spent at IIT Madras. So, what I feel a researcher should be is three qualities I feel a PhD student should possess. I hope all of you have this. First and foremost, you should be able to go for a cup of tea with your friends and talk about research. Not a cricket match, not a IPL match, anything of that sort, or not a new Shah Rukh Khan movie that has come, but research. Second, I feel you should be able to go to bed thinking about the problem that you are solving. But I can confidently tell you, many a times you get solutions in your dreams. And I am standing example in front of you. I got many solutions for my problems. Uh, Third, and more important, uh, anybody, if he or she is not excited about her or his research, they should not do research. Okay? Excitement, the joy. Uh, First and foremost is nobody will get a PhD if you are solving a problem that has already been solved, right? We all know this. Okay? So that means, at least to the best of your knowledge, within the literature that you have studied, uh, you are solving a problem which nobody else has solved it. That should give a kick in you. Hmm? That you should be able to catch hold of a 12th standard kid and make that kid excited about your work. If you can't do this, I would say we should drop off our research and go somewhere else. I always say this, whatever you do, if you can't enjoy, I tell all my students, 56 students I have graduated till today, and I tell every one of them that you people should choose a job where you don't wait for a Saturday, Sunday. And a Sunday night, if you are worried that tomorrow is Monday, how much ever money you are getting from that profession, from the job, it's better to leave that job and find what your heart wants you to do. And I have found this. Okay. I'm very clear in my mind. I did not even attend a campus interview when I finished my BTech. I had to actually give it in writing because those days very few companies used to come. I'm talking of 1986 when most of you are not born, apparently, excepting possibly a few front row guys. Uh, so uh, I had to give it in writing that I'm not interested. Mm. And so that the second topper, third topper of my class can actually get their job. So this is was very clear to me. And then, you know, I asked my guide, BTech guide, what is the best place I should do? I mean, first of all, I asked him, sir, what should I do to become a teacher like you? He said, Murthy, you should do a PhD, he said. And then I asked him, where? He said, there's no place better than IIC Bangalore. That's it. Those days, there is nothing called direct PhD. I had to do an MTech to do a PhD. And some of my senior told, unless you have a 9 point IIC. So my goal got set and I worked hard. I come from a very different background than many of you. I have done a diploma in metallurgy, Polytechnic, okay, where nobody teaches you maths and physics. And then I joined REC Nagpur, which is now called VNIT now, into second year directly, which is called lateral entry. That means you have finished, you have skipped the first year maths and physics. Okay, so I I thought, how can I become a teacher without knowing maths and physics? Uh, So deliberately picked up those days gate exam. I don't think any of you, some of the people in the front row may know that we used to have two gate papers. Okay, one is your own branch. Second is called a bunch of 11 subjects, out of which you have to pick up 5 subjects. Choice is yours, and it's a huge question paper they give of 11 subjects. You pick up any 5 and answer those 5. And I picked up physics and maths. Spent 6 months to learn engineering maths and engineering physics uh, deliberately, and then went ahead and got whatever is the necessary percentile that I needed to join IIC Bangalore. So, what is important, friends, in life is to first believe in yourself. Okay, this is very, very important, and aspire. Uh, somebody, I do not know whether you have heard of this gentleman, a gentleman who started HCL. You all know HCL, the first computer company in India. 1979 or so, it came into existence. And one of those gentlemen who was a part of that group which has started HCL wrote a book very recently called Just Aspire. Anybody has heard of this book? Raise hands. No, you are all too serious researcher. Don't read anything beyond your research. Okay, so please, if you get a chance, read that book. And I attended the book launching ceremony. Okay, the book says Just Aspire. Okay, and he said in that talk that A is significantly greater than R. Can somebody guess what is this A? What is this R that we are talking about? R is louder. Result. Very good. Somebody else? Reality. Very good. Somebody else? Reaching. Okay. Anyone? Responsibility, somebody said, I think. Okay. Anyway, so his word was different. You see, this is all like the define machine in 3 Idiots that fellow asked, right? You have to answer what he is there in his mind. But anyway, so I have nothing in my mind. I am just repeating what he has told. He said, A obviously is aspirations. And many a times we say, I have big aspirations, but my resources are poor. Mostly these faculty who sit in the front rows, they always say that. I mean, while PhD students also say this, they go to the director, you give me that, you give me this, then I will show you. So he says, if your aspirations are like an Everest mountain, opportunities and resources will come and knock your door, is what he says. I'm also a strong believer of that. One should have great aspirations. I mean, my dreams, I don't sleep at all much. So I have enormous dreams, and all of you friends, it's very, very important to have big dreams. But the dreams supported by your will to work towards the dreams. As Abdul Kalam says, that you should not be willing to sleep until the dream is achieved. And this needs a lot of self-confidence. I'll give you one example and close, where we did not have good self-confidence and lost somewhere, and somebody else had that self-confidence and won it somewhere. I'm talking about a field where I started my research. It's called quasi-crystals. I do not know if any of physicists or chemists sitting here have heard of this. Okay, quasi-crystals are supposed to be crystals which have special symmetries. Okay, you all must have heard of symmetry. If you have heard of symmetry, there is two-fold symmetry, three-fold symmetry, four-fold symmetry we talk about. There are certain symmetries which are called forbidden symmetries. Five-fold symmetry is a forbidden symmetry. And there's one gentleman in 1982 working on some aluminum alloys, and he prepared an alloy. He wanted to make high-strength aluminum alloys, a metallurgist, and put it into a microscope. And he was looking at the microstructure of that particular sample, and suddenly found out a precipitate. And when he was taking a electron diffraction from that precipitate, he suddenly saw the diffraction pattern had a five-fold symmetry. He said, wow, okay. Nobody has ever seen such a symmetry until then. And he went to his supervisor. Uh, he was working in, which place was this? Uh, uh, I think Caltech. Suddenly skipping my mind. Okay, the person with whom he was working was very famous metallurgist, and then his boss or his supervisor did not believe him. So obviously, it's not easy to believe anything new that you come across and then tell and go and tell your guide. Most of the guides will not believe. So he kept on working hard and doing a number of such samples, and every time he saw a similar diffraction pattern, and he started talking about it in talks like this, and many people did not believe, to the extent that there is a great chemist those days who got 2 Nobel Prizes, Linus Pauling. Hmm? So Linus Pauling made a statement saying that there are only quasi-scientists, no quasi-crystals. Okay, and his own supervisor said, "You are bringing disgrace to our group. I want you to leave my group." Then he did not give up. Okay, kept on working hard, and then a few other people started working on similar systems and started seeing the similar results. 82, when he published his paper, nobody published his paper. When he went to a few mathematicians and asked them this question, why is it I am seeing? It's not that it is something a dream, it is a reality. It's there in front of my eyes. Then they demonstrated through mathematics, saying that if your atomic arrangement in your materials is not periodic, but if it is quasi-periodic, okay, like a Fibonacci sequence, we know, its Fibonacci sequence is never periodic. You add the previous 2 numbers, you get the next. Let's say if your atoms are arranged in such a way that the distances between atoms follow something like a Fibonacci sequence. In such a case, your diffraction pattern from such a material would have a quasi-periodicity, is something mathematically they have proven. And then in 84, his paper got accepted. And then in 2011, he gets a Nobel Prize. The only Nobel Prize that any metallurgist has ever got is that Nobel Prize. His name is Dan Shetman. He comes from, Egypt. What is that university? Very famous university in Egypt. Technion. Technion. Sorry. Thank you very much. So, but what is more important, that gives you one lesson, that if you do not give up, believe in yourself in spite of your supervisor not accepting what you are saying, one day you will make the whole world believe in you. Okay, and he has made this to such an extent, International Crystallographers Society had to change the definition of crystal itself. Until then they believed crystal is something which has both translational symmetry and rotational symmetry, and then they changed their definition and said a crystal is one which has a definite definite diffraction pattern, which demonstrates some symmetry. So, this is something, friends. Every one of you should have this. Second is another story from India. 1978, a group from Banaras Hindu University from Metallurgy Department published a paper showing a five-fold symmetry in one of the alloys that they are working on, again from Metallurgy Department. Those people were PhD students at that time. They are all senior professors, retired now. Some of the names that I know, Professor Ramchandra Rao, he was the Vice Chancellor of Banaras Hindu University, sometime passed away, some time back. Professor C. Suryanarayana, he is a very famous metallurgist from Idaho. He stays there in US. So, but what is important again is they took this to their supervisor. The supervisor again did not believe. And while he allowed them to publish the paper, please remember, this is 1978, I am telling you. 6 years before Dan Shetman published his paper in 1984. still we never got a Nobel Prize. Why? Because these people, okay, have not continued, did not write a large number of papers, beating it left and right. Why? Again, in India, we follow our supervisors too much rather than following our own intuitions. So this is something, friends, we lost a Nobel Prize. While we can call ourselves as pioneers in publishing the first paper in this particular field, we did not get a Nobel Prize which somebody else has got. So please, friends, have self-confidence in you. Whatever you are working on, believe in yourself. When I started my research on something called mechanical alloying, everybody said you are doing some dirty job. Mechanical alloying is to some extent dirty job because you take powder, put it into a ball mill, and then shake it, and something happens to it, and you get some nanoparticles out of it. I didn't give up. After close to 10 years, now every institution in India, whichever is doing material science, they do that. Okay, and that gives me a satisfaction that I never gave up, but I picked it up. So similarly, friends, okay, I request all of you, if there is a parting message from me, believe in yourself. Believe in yourself. There is so much of talent in each of you. Not just because you are PMRF, I am telling you. Every individual has that so much. It's like, can you see a huge tree inside a seed is what characterizes you. The seed is too small, but are you able to see a big tree inside that? If you can see inside that, then I would say you are a strong, positive fellow, and and such a belief you should have within you first of all. Okay, so all the best to all of you. Thanks for coming to IIT Hyderabad once again. I hope you had wonderful time last 2 days, and I wish you all the best. Thank you very much.
Thank you, sir, for that engaging and informative talk. It leaves us with valuable insights and inspiration. Now we will be moving forward with our closing ceremony. A big thank you to all our esteemed speakers for their brilliant contributions. And we would like to take a moment to thank everyone who made this symposium possible. And we will have the closing ceremony now. We had 2 wonderful days listening to the esteemed speakers and learning from the posters of our fellow PMRF scholars. Now, I would request our director, sir, Professor B.S. Murthy, to please give awards to the poster presentation winners. So, from computer science, it is poster number 122, Abhinav Joshi from IIT Kanpur. From chemical engineering, it is poster number 148, Abhash Anand from IIT Delhi. From civil engineering, earth science, architecture, ocean and naval engineering, it is poster number 26, G. Saravanam from NIT Tiruchirappalli. From electrical engineering and electronics, it is poster number 106, Himanshu Bhushan Sandhibi Graha from IISc Bangalore. From mechanical engineering, aerospace engineering and design, it is poster number 78, Pasunuru Sai Vineet from IIT Madras. From biomedical engineering, biological sciences and agricultural science, it is poster number 27, Jagriti M. Patil from IIT Gandhinagar. From material science and metallurgical engineering, it is poster number 35, Tausif Anwar from IIT Madras. From physics, it is poster number 48, Devdeep Brahma from IIT Kharagpur. From chemistry, it is poster number 87, Preeti Bhatt from IISc Bangalore. From interdisciplinary area in science and engineering, it is poster number 133, Deepak Sharma from IISc Bangalore. Thank you, sir, for giving away the poster awards, and a big round of applause for all the presenters and winners. I would now request Professor Kishalay Mitra to please come to the stage and deliver the vote of thanks.
Good afternoon, everyone. So, on behalf of the organizing committee and all the participants, I extend my deepest gratitude to everyone who contributed to making this event a grand success. First and foremost, I would like to express sincere thanks to our chief guest, Dr. V.K. Saraswat, Honorable Member, Niti Aayog, Government of India, for gracing this occasion despite his busy schedule. His inspiring words and profound insights have truly enlightened us and set the tone for continued academic excellence and innovation. A heartfelt note of gratitude goes to Professor B.S. Murthy, Director IIT Hyderabad, for his visionary leadership, continuous encouragement, and unwavering support in hosting this symposium. We are also immensely grateful to all distinguished speakers who shared their valuable knowledge and expertise through the plenary lectures. To our PMRF scholars, your presentations reflected the remarkable breadth, depth, and impact of the research being undertaken under the PMRF scheme. Hope you enjoyed sharing your work with your peers as well as experts from different corners of the country. Our sincere appreciation also goes to the esteemed faculty members who judged the poster sessions. A special word of thanks to the organizing team and volunteers, Professors Mubala Gopi, Preetha Chatterjee, Sweta Yadav, Shlaka Gupta, Mayur Vaidya, Saurabh Singh, Venkatrao Kotagiri, Deepu Babu, and Chandra Murapakka for your tireless efforts behind the scenes. From planning to logistics, your dedication ensured the seamless execution of this event. Our heartfelt thanks also to the Convention Center team for their constant support and assistance in every possible way. A sincere thanks to administrative supports provided by the academics as well as the account section standing as a backbone for PMRF cell at IIT Hyderabad. A deep gratitude to the Ministry of Education and the PMRF National Coordinating Committee and the IIT Madras team for their continuous support and collaborative spirit that made us feel that IIT Madras was right beside us throughout this journey. Thank you all once again, wishing you continuous success in your research pursuits, and I hope you thoroughly enjoyed every moment of this symposium. Given a chance, we hope to see you again at the same venue in the future. Thank you. Wish you all the best.
Can we all have one group photo? Come onto the dais. You can also join. You can also join. Whoever on the top, you can come onto the dais. We will wait for you. So the first row will be sitting, second row will be kneel downing, third row will be standing.
IIT Gandhinagar, you wanted to take? All the volunteers, please come on stage once. We'll take one more photograph.
Only volunteers.